Can you see that? And what did the people use in the morning? Right, but this is... Okay, we're going to hold off for 5 minutes. Let people come back from lunch. Michael? Could you come over? That could mean a lot of people in the audience. So we're going to use a different point as well. Oh, all right. Then I'll bring this back. Right. Thank you.
Yes, you do, but I mean, well, actually, they're open all day. No problem. So that's good. Okay. That qualifies.
I should tell you my mother.
All right, I can see the folks are coming back. So good afternoon, everyone. Welcome to the beginning of the afternoon session. My name is Peter Maximovich. I'll be chairing the first part of the afternoon session, where we have two invited talks, one theoretical, one experimental, and a contributed experimental talk. Our first speaker today is Nick Bristow from the Imperial College of London. And Nick is going to tell us about coupling and electrical control of structural optical magnetic orders in perovskites.
Okay, good afternoon, everyone. Hope you've had a good lunch. It's a great pleasure to be here and to be able to talk to you today. So yes, I'd like to talk about electric field control of electronic properties of materials, and that's the main motivation for today's talk. And the strategy that we're going to propose is utilizing lattice mode couplings that we've talked about in the morning session, so the idea of hybrid improper ferroelectricity. We're going to apply this strategy to the perovskite system, since they show quite an unusual coupling between the various degrees of freedom inherent in these systems, so the structural and the electronic degrees of freedom, which can be subcategorized into the spin, charge, and orbital degrees of freedom. So I'm not going to go into too many details about the trilinear coupling term, because I think we've heard a lot about that this morning. But just to summarize very briefly, typically in perovskite systems, there can be a trilinear coupling between the polar mode and often two tilts, because the tilts are quite common in the perovskites, they're fairly ubiquitous. And the tilts, for example, might be out of phase, or they could be in phase. And the idea is if you apply an electric field, the dielectric effect, you can tune the polar mode. That in turn can then tune the magnitude of the different tilts. And just to mention that this kind of trilinear term involving a polar mode typically involves extra symmetry breaking, typically by layering the perovskite, as we've seen this morning, either in a superlattice form or a double perovskite, or in naturally layered perovskite compounds such as the Rudolphson-Popper series, which you've already also heard about this morning. And we've seen presentations which have shown some kind of experimental signatures for the existence of this trilinear coupling term. So I think it really is a promising avenue to work on, and it's a real effect. So the idea of today's talk is actually, well, let's see if we can engineer a different type of trilinear coupling, now involving the polar mode, but perhaps different lattice modes, which might couple to electronic degrees of freedom perhaps more strongly or slightly differently. And the obvious mode to choose, perhaps for the perovskites, is what's called the Jahn-Teller distortion. And so this is also, I'm going to focus on what's been called the Q2 distortion, which is an orthorhombic distortion. And around the octahedral cage, it creates two long bond lengths, two short and two medium. And this can often arise to remove an electronic degeneracy in Jahn-Teller active systems. So for example, in manganese 3+, which has a D4 occupancy, it often appears, for example, in lanthanum manganite, to split the EG levels and open a band gap and lower the electronic energy of the system. So this Q2 mode is a local mode, but it can order at different Q points. So for example, the most common obviously is the M point. This is a half-half zero, which then appears as a kind of in-phase pattern between alternate 001 planes, or at the R point, which appears antiphase, so at a half, a half, a half. And then you can obviously imagine that you then get kind of an in-phase orbital ordering out of plane between 001 planes, or an antiphase type orbital ordering. And then through super-exchange interactions, you might imagine that you could also have different spin orderings as well. So that's the idea of today's talk. Can we find some trilinear couplings which involve a polar mode and one or more Jahn-Teller distortions, so that if we apply electric field, we tune the polar mode, and in turn tune the Jahn-Teller distortions, which can then in turn perhaps tune the orbital or the magnetic degrees of freedom in these systems. The obvious application is magnetoelectrics, but perhaps this could be useful for other types of electronic devices, since the Jahn-Teller distortion can also tune the band gap. So for example, electrochromic devices, maybe metal insulator transitions and transistors. And just to mention that a very similar mechanism has also been proposed recently in the literature by the group of Silvia Picozzi and co-workers in metal organic framework systems, where they've actually shown that there is indeed an application for potential magnetoelectric effects. Okay, so just to mention before I show some results that the ion teledistortion, as I call it, doesn't have to be actually electronically driven. It can itself appear as a lattice-driven mode, again due to a trilinear coupling term. So for example, in the PNMA perovskite system, this is the most common tilt pattern in perovskites, there is actually a trilinear coupling term involving one of the tilts, an antipolar mode appearing at the X point, and then finally this ion teledistortion at the M point of the Brillouin zone. And so even in non-ion teleactive system without any d electrons, this term will automatically force the appearance of the ion teledistortion at the endpoint. Even if the coupling coefficient might be very small, it might only be a very small mode, but it has to appear in PNMA systems. So here, I'm going to term a ion teledistortion simply by the symmetry of the mode. And in some cases, it might appear electronically driven. In other cases, it might appear as lattice-driven. But in both cases, I'm going to call it a ion teledistortion. Okay, so let me highlight 3 different examples in today's talks. Superlattices, both of tisonate systems and validate systems. And finally, I want to mention some results on bulk perovskites. In all cases, we perform density functional theory calculations. In some cases, they're on magnetic systems, so we need to be a little bit careful about the exchange correlation functional. And we choose PBE Sol plus U, where U is this on-site Coulomb repulsion, or hybrid functionals, and depending on the system that we were interested in. So, for example, if we have experimental data to compare with, we might choose the GGA plus U approach and fit the U to experimental data. If we're predicting new systems and for example, in superlattices, we don't have experimental data, we might choose the hybrid functional. Before I go into the results, let me just mention the collaborators that have been involved in this work. So particularly the leaders of the groups in University of Liège, Philippe Gauzet and Eric Bousquet. Also Denis Fontaine and Julianne Varignon, who's now in Paris. So the tisonate systems is the first example. So this is a superlattice that we're considering of A and R cations. A is divalent, R is trivalent. And so on average, the titanium deoccupancy is half an electron. And let me go straight to the result that we find from our DFT calculations. In all these chemistries that we studied, we actually found a very low symmetry polar space group. The system happened to be electrically insulating and was also ferroelectric and unusually ferromagnetic as well. So let me first go through the structure. So it's quite a low symmetry structure involving quite a complex distortion. We decided to perform a symmetry adapted mode analysis where we decompose this global distortion in terms of the different irreducible representations. Here I've just denoted them by symbols so that we can kind of view them pictorially. So first of all, the tilts show the largest amplitude in the distortion, and this makes up the well-known PNMA-like tilt pattern. And then through the trilinear coupling terms that we've already talked about this morning, this induces the polar mode, which we find is the second largest distortion. And we calculate actually a spontaneous polarization, which in some cases can be quite large, so that approaching barium tisonate, nearly 25 microcoulombs per centimeter squared. So that's quite unusual, I think, for an improper ferroelectrics. But we can understand the origin of that as the fact that it's a ferry-like motion between the A and the R planes, which move in the plane. And so we can maximize the polarity of that mode by choosing a small trivalent cation, which has typically a larger Born effective charge, and a larger divalent cation, and that's indeed the case for thulium barium tisonate. So for it to be ferroelectric, it also needs to be obviously electrically insulating, and correspondingly we see a breathing mode, because normally we might not expect the system to be insulating with half the electron per site. This breathing mode consists of expansion and contraction of neighboring octahedra, and this lifts the degeneracy between the neighboring titanium sites, allowing for a D1, D0-like charge ordering. So let's have a little look at the electronic structure in more detail. Here I'm showing the density of states, which is spin polarized up and down. You can see there's a small band gap for this particular chemistry, and there's a spin polarized split-off band just below the Fermi level. This is the state which is responsible for the magnetism. The major weight on this state is coming from what I call the D1 titanium sites. These are the sites which have the expanded octahedra. And on these sites, we have an XZ or YZ orbital ordering on neighboring O1 planes. But this isn't the whole story. It's not exactly D1, D0. In nature, there is some hybridization onto the D0 sites. And on these sites, we have a mixed XZ and YZ orbital ordering. So this is the global orbital ordering that we see. And we think we can understand the origin of this orbital ordering by the fact that we see as our fifth lattice distortion a Jahn-Teller distortion, the one that we're searching for. This is the Jahn-Teller distortion appearing at the endpoint of the Brillouin zone. It might appear as an electronically driven, or it could indeed be lattice driven, because we actually see that there is a trilinear coupling term. This is equivalent to the trilinear coupling term that appeared in the PNMA phase, but now we're just breaking the symmetry, and the anti-ferroelectric mode is becoming polar in nature. But this suggests that the tilts can induce the polar mode, which can induce the Jahn-Teller mode, which can allow for this type of XZ, YZ orbital ordering in the plane, which is repeated out of plane. And then on top of that, we have the charge ordering, which allows for this XZ, YZ orbital ordering between neighboring O1 planes. So I mentioned that in all cases we found from the DFT calculations a ferromagnetic ground state, which is quite unusual, I think, for insulators. So we wanted to try and understand the origin of this ferromagnetism, and just to try and summarize very quickly our current understanding. So, as I mentioned, we already have this XZ, YZ orbital ordering on the two D1 sites. These are the D1 sites shown here, and this is the D0 site. So, all of the YZ orbitals are coming from the same band. It's the same electron. So, if we choose an upspin here, we have to choose an upspin on the D0 site as well. Same with the XZ orbital. We could obviously choose an anti-alignment between here and here, but due to Hund's rules on the site, we want to maximize the spin between different orbitals, and so that's the origin that we think is creating the ferromagnetism in this instance. It's essentially Coulombic repulsion in nature. We found, though, that the Jahn-Teller distortion was crucial for the observed ferromagnetism. Indeed, that if we suppress the tilts, and with it the Jahn-Teller distortion through this trilinear coupling term, and also the ferroelectricity, we find XY orbital ordering everywhere in the superlattice, so no longer XZ, YZ. And indeed, when we perform the DFT calculations, we find an anti-ferromagnetic ground state, no longer ferromagnetic. And we think that we can understand the reason behind this. Now we've got the same orbital occupied everywhere. On the site, due to Pauli-'s exclusion principle, we want to anti-line the spins. So this now suggests that if we apply an electric field to the system, perhaps through this trilinear coupling term, we could tune the magnitude of the Jahn-Teller distortion, and perhaps go from one of these two states, and perhaps kind of turn off and on the ferromagnetism. I mean, that's speculation, but that's a potential application for this kind of trilinear coupling term. So that's the titanate system. Now I'm going to go on to the vanidates. So again, 1-1 superlattices. Now these are the rare earth vanidates. So let me just go through the bulk system briefly. So the rare earth vanidates show typically two different symmetries depending on the size of the rare earth cation. Either a PNMA ground state, which allows for this M Jahn-Teller distortion, which has a C-type orbital ordering and a G-type anti-ferromagnetic ordering. On the other hand, with larger rare earth cations, there is this P21C space group, which has actually the R Jahn-Teller now involved, which breaks the symmetry slightly, and allows for a G-type orbital ordering and a C-type magnetic ordering. So let's see now what happens if we make a superlattice. So we performed DFT calculations on a few different superlattice chemistries. And depending on the size of the cations, we found that the ground state was either a PB21M phase, which is the same as the PNMA phase, but now with additional symmetry breaking due to the layering, or a PB phase, which now has additional symmetry breaking. It's the same as the P21C phase, essentially, but additional symmetry breaking due to the layering again. So we can perform a symmetry-adapted mode analysis again to look at the different modes which appear in these phases. Indeed, we find in the PNMA-like phase the tilts, the M Jahn-Teller distortion, and an in-plane polarization, as you'd expect. Now, for the PB phase, we see additional modes which appear, but the original modes don't disappear. So we find, additionally, with the M Jahn-Teller distortion remaining, we find now the R Jahn-Teller distortion on top of that, which appears, and also a very small outer plane polarization, which we calculate to be of the order of about 0.5 microcoulombs per centimeter squared. So let's try and understand the origin of these different modes. So in blue, I'm showing the two trilinear coupling terms which you already know about from the tisonates. This appears in the PB2M phase. So we have the tilts, which form the PNMA-like tilt pattern, which can induce the in-plane polarization, and in turn can induce the Jahn-Teller mode, although I think in this case the Jahn-Teller mode is already electronically driven. In some cases in the validates, the R Jahn-Teller wants to come in, I think due to the Jahn-Teller effect. But the M Jahn-Teller is now pinned into the system due to the two top trilinear terms remaining. So now we're forced to have the combination of both Jahn-Teller distortions in the superlattice, and we find a new trilinear coupling term involving the two Jahn-Teller distortions and an out-of-plane polarization. So this opens the question, well, let's see what might happen if you apply an electric field. So we considered a particular chemistry now which actually had the PNMA-like phase. So this is just involving the modes in blue. So this is the yttrium lanthanum vanadate system. So the phase which doesn't have the out-of-plane polarization. But now if we apply an electric field out of plane, through the dielectric effect, we obviously induce an out-of-plane polarization. Then due to the fact we've got this trilinear coupling term, this will in turn induce an R Jahn-Teller mode. And this R Jahn-Teller mode will in some sense compete with the M Jahn-Teller distortion, and perhaps at some critical fields we might change from a C-type orbital ordering to a G-type orbital ordering, and that in turn could affect the magnetic properties of the system. And so we actually performed finite electric field calculations, essentially using the frozen phonon method, whereby we considered this yttrium lanthanum vanadate system, which had the PB2M ground state, so the phase which doesn't have the outer plane polarization. We applied an electric field. We calculated the free energy difference between the two phases. So we actually looked at electric field in both phases simultaneously. And at some critical field, the system indeed wants to switch from the PB2M to the PB phase, and with it switch from a G-type magnetic ordering to a C-type magnetic ordering. So we possibly might have a system here where we have an electric field-induced magnetic phase transition, which is, we believe, to be due to the fact that we are indeed tuning the magnitude of the R Jahn-Teller distortion with an electric field due to this trilinear coupling term. Okay, so let me just finish the talk with one last example of a coupling between the polar mode and a Jahn-Teller distortion. So the idea now is, well, this is all very well and good. Oh, that's not good at all. Sorry about that. So the idea now is that, well, okay, so far we've illustrated a trilinear coupling term between a polar mode and a Jahn-Teller distortion in superlattices, but experimentally it's a little bit tricky to grow these 1-1 superlattices, as you might imagine. And so can we kind of generalize this concept and perhaps find a trilinear coupling term in bulk perovskites? So we obviously need to find the polar phase, and the obvious route is strain engineering, as we've already heard about this morning. And so, looking through the literature, we spotted a few publications whereby we see that a polar phase with strain engineering in bulk perovskite systems, which is fairly unusual, and it appears to be quite general. So in this PRL of 2012 from the group of Laurent Belesch and Max Stengel, they found this phase to be the ground state for several chemistries at a roughly 5% tensile strain plus or minus a couple, depending on the exact system. In addition to having the polar mode in the ground state, they also found the existence of an antipolar mode and a tilt, and quite an unusual, what they call an orbital ordering that exists in the system. So this is, for bismuth ferrite, this is D5. It's not an ordering of the occupation of the orbitals, but instead an ordering of the states. And so, as you can see, for different ion sites in the perovskite, you have a different ordering of the XZ, YZ, and XY orbitals in the density of states. Later on, in 2014, there was observed to be a trilinear coupling between the polar mode, this antipolar mode, and the tilt, but no mention so far of any Jahn-Teller distortion. So we thought we'd revisit this phase and see if it was truly general. So we wanted to look at several perovskite systems with different D fillings, so D0, D3, D5, and D4, strontium titanate, barium manganate, bismuth ferrite, yttrium manganite. And we searched with tensile strain, we searched for different phases. We indeed found that at a critical tensile strain, we have this PMC21 phase. And when we do a symmetry mode analysis, we indeed find the three aforementioned modes, so the polar mode, antipolar mode, and tilt, but we find a fourth mode, which was previously not mentioned, and this is the desired Jahn-Teller mode. And it's large, so it's of the same magnitude actually as that of lanthanum manganite, which is kind of a prototypical Jahn-Teller system. So why do these modes develop? It's indeed due to a trilinear coupling term between the polar mode, the Jahn-Teller mode, and now the antipolar mode. So this is the kind of coupling that we want, and we think that it's general, and it appears for PMC21 perovskites, which appears to be quite a general phase under tensile strain. So it's interesting to just consider briefly what are the primary modes, what are the secondary modes, and so we can compute the potentials for the different modes, for the four different chemistries, and what is the primary mode depends on the system. So it appears that for small tolerance factor systems such as yttrium manganite and bismuth ferrite, the tilt appears to be the unstable mode, which drives the system to the PMC21 phase. On the other hand, for larger tolerance factor systems such as strontium titanate and barium manganite, it appears that the polar mode is instead unstable. In addition, for yttrium manganite, which is Jahn-Teller active, it's D4. The Jahn-Teller mode is also unstable as well. So okay, so how can we use this? Well, let's try applying an electric field now in plane to try and tune this trilinear coupling term and hence tune the Jahn-Teller mode. And we indeed find that we can tune the Jahn-Teller mode with an applied electric field in plane. And you might look at various properties. We decide to look at the band gap. And for the case of yttrium manganite especially, we find a fairly large change in the band gap, as you might imagine, because it's Jahn-Teller active. Okay, so let me just summarize the talk. Hopefully I've convinced you that a trilinear coupling term involving the polar mode and Jahn-Teller distortions might be interesting to look at for functional applications. And I've highlighted three different examples whereby we find these types of trilinear couplings. And with that, I'd just like to thank again my collaborators at the University of Liège, and thank you for your attention.
Talk is open for questions.
The last case you mentioned yttrium manganite and barium manganite. You assume perovskites or hexagonal systems?
So we assume the perovskite system. I agree that under zero strain, the perovskite system is, but under tensile strain, I think there have been some theoretical calculations which suggest that it can become perovskite. And that's the tensile strain regime is where we're looking at now. So, but this is more, we're illustrating a concept. I'm not going to try and claim that necessarily these are the exact systems which might form devices, but just for the purpose of illustrating the concept, we looked at the perovskite phase.
So if I understood, the mechanism you show would be the same even if you had just local moments as well as if you had ordered moments. I mean, so the question I have is, how can you tell how strong the coupling would be in terms of the, you keep the local moments, but you just order them or change them as opposed to, in other words, you have a very strong coupling to the local magnetic structure, but how much is there to the amount of magnetic order?
Well, first of all, this effect is there actually for even non-magnetic systems. So it's purely from the symmetry. So even in non-Jahn-Teller active systems, D0 filling, we're going to have these couplings. They might not be as useful. for magnetic systems, especially ones which are Jahn-Teller active, it's you know, I don't see it as a local type of thing. I think it's a frozen distortion which appears, you know, either at the end point or the R point, is what I've mentioned here, and that can influence the ordering of the orbitals, and hence through super exchange interactions, the ordering of the magnetic ground state phase.
What I'm saying is that
Yeah.
you can have locally ordering of the orbitals,
Mhm.
but what you're requiring is global ordering of them. I mean, so it's the difference in energy between the disordered, you know, system of a given local symmetry, say, and the ordered one that maybe matters, accompanying with the amount of ordering. So that might be a much different effect than the local orbital ordering.
Yeah, I'm not considered disordered. Sorry, no, it's my fault. I'm not considered disordered.
Would it work on a nanoparticle?
Sorry?
Would it work on a nanoparticle?
I don't know.
Any other questions? Can I ask another question?
Sure.
It looks like the fields that are required to influence these structures could be as high as a few megavolts per centimeter. Since the band gap of the system is fairly small, would that be a problem with sort of intrinsic Zener breakdown of some sort?
Yeah, you're right. So for the particular chemistries we looked at, the critical field to switch between one magnetic phase to another could be large, and I think, you know, for a few layers you would get a breakdown. So realistically, the field is too big. But you can imagine tuning the chemistries to tune the energy difference between the two different metastable phases, for example. That might lower the critical field. Another thing which we didn't consider here is non-collinear spins. So in some of these phases there is weak ferromagnetism, so there might just be a linear magnetoelectric effect rather than a switching between phases. So that could also be useful. Yeah.
Yep. Next speaker. Okay, next speaker is Alexander Gruter from National Institute of Science and Technology, and the title of the talk is probably magnetoelectric heterostructures with polarized neutron reflectometer.
Oh, was it there? I'm never patient enough. Yes, okay, good. Thank you. I'd like to thank the organizers for the opportunity to be here today and talk to you. Right off the bat, I sort of want to give a disclosure that this talk is going to be a little bit different in that I'm not really a ferroelectrics person. As you might surmise from the NIST Center for Neutron Research logo, I'm primarily a neutron scatterer. And so today I'm going to be taking you through some of our work in probing magnetoelectric heterostructures with polarized neutron reflectometry. So although I'm not necessarily a ferroelectric specialist, I think we share a lot of interest, in particular in the area of magnetoelectrics and perovskite structures, complex oxide thin films, and interfaces. And so before we get into that, I have a lot of collaborators that I would like to thank for all of their help in making this work possible. In particular, Dustin Gilbert, Brian Kirby, Julie Borchers, and Brian Moranville at the NIST Center for Neutron Research. At Stanford University, Arturas Velionis and the Suzuki Lab. At the Advanced Light Source at Lawrence Berkeley National Lab, Elke Arenholtz, Alpha Nadai, and Patrick Schaefer. And at UC Davis, Kai Lu. So probably the best thing to start out with here, since I suspect not a lot of you have done neutron reflectometry, is what is polarized neutron reflectometry and what does it tell us about magnetoelectric systems? So the easiest, or there are several methods by which we can get neutrons. Possibly the simplest, or at least the one we use at the Center for Neutron Research, is step one, build a nuclear reactor. Step two is basically cut a hole in the side of the reactor and let the neutrons come out and put your sample in front of them. It's a little bit more complicated than that, but at the most fundamental level, that's what we do. So you have your neutron, it comes in and reflects off of, in this case, say a thin film sample. goes into your detector, and you get some sort of spectra that looks like this, where you have an intensity versus angle or an intensity versus scattering vector plot. And from this, you can get things like composition or thickness from your films. Now, you can do a lot of the same sort of thing with X-ray reflectometry, but neutrons have a couple of really nice advantages. So the first one that I want to point out is that neutrons are spin sensitive. Neutrons have spin up or spin down. And so that means if you have a magnetic structure, you can take a spin polarized beam of neutrons, and you get two separate intensity versus angle or intensity versus reciprocal lattice vector curves here, one for spin up and one for spin down. And if you have a magnetic system, those two curves are going to be different. And so what we can get from polarized neutron reflectometry based on the differences and based on the scattered intensity is the nuclear and compositional depth profile of your thin film. You can get the magnetic depth profile, and in particular, another nice advantage of neutron scattering is that we're very, very much insensitive to magnetic contamination. So if you've done any sort of nanoscale magnetic studies, you know that iron oxide and other magnetic contaminants are basically everywhere, and as soon as you get the tiniest little speck of magnetic contamination on your surface, it immediately swamps out the signal coming from your thin film. So the nice thing about neutron reflectometry is that we only see shiny things. Essentially, if you can see your reflection in the surface of your film, you're going to get a nice reflectometry spectra out of it. But the little dust particles, the little magnetic contaminants from, say, your tweezers, they don't reflect, and so we don't see them. So throughout this talk, there's two ways I'm going to be presenting this data. One of them is your basic intensity versus reciprocal lattice vector plot, where you see, splitting between the two spin states. The other way is what we call the spin asymmetry, where you take the spin down intensity, you subtract it from the spin up intensity, and then you normalize it by the sum of the two. And so this is basically just a way of really enhancing and showcasing the magnetic contributions to your scattering. So we get some data. Usually this is how this works. We get some data. We have some idea of a model that will describe it. From that, we can actually explicitly calculate the expected reflectivity curve from our samples, compare it to the data, and spend a lot of time trying to make those two look the same. And hopefully we end up with something that matches about this well. And from that, we reconstruct a scattering length density profile, which gives you your composition here from the nuclear scattering length density in black, and your magnetic scattering length density here in red. And so you can see which parts of your film are magnetic, whether that changes, and also back out your structure. So as we been able to apply polarized neutron reflectometry to studying magnetoelectric heterostructures in complex oxide perovskite interfaces and also metal oxide interfaces. So we'll start with the perovskite systems, and as I'm sure most of you are very well aware, given the content of today's talks already, so I'll make this brief. In perovskite thin films and heterostructures, we have a lot of different A-site cations, a lot of different transition metals on the B site. It doesn't necessarily even have to be a transition metal, and a nice octahedral cage of oxygen. And because we have a strongly correlated electronic system, and we have all sorts of different atomic species and valence fillings, we end up with a wide range of magnetic and electronic ground states in these heterostructures. When you combine this with the fact that in the last maybe 20 years or so, thin film deposition techniques have advanced to the point that we can get really high quality superlattices and interfaces that are grown with atomically precise thickness control, we can stabilize a lot of functionalities that are just not observed in the bulk system. So the example that I'm going to spend the first half of this talk on is the calcium ruthenate, calcium manganite interface. So our calcium manganite system is a pretty standard G-type antiferromagnetic insulator. If you look at the spins on the manganese ions, it looks basically like this, until you grow it next to calcium ruthenate, which is a paramagnetic metal, and then you end up with some sort of ferromagnetic behavior. So this is a magnetization versus applied field hysteresis loop for a calcium ruthenate, calcium manganite superlattice. The really important feature to take away from this is that it saturates at 1 Bohr magneton per interfacial manganese ion. this is actually really, really low. So what you would expect from a fully magnetic layer at the interface is something like 3 Bohr magnetons. And in fact, we don't even know for sure if this is all at the interface or if it's spread out throughout the entire calcium manganite layer, in which case our normalized moment per manganese is even lower. So the first sort of question that we can answer with neutron reflectometry is, what is the ferromagnetic layer thickness? And this is the kind of way we approach this sort of problem is we get a nice neutron reflectometry spectra, looks something like this. We use the superlattice, so we get these nice Bragg peaks here and here. And if you look at the theoretical calculations, depending on the thickness of the magnetic layer at the interface, whether it's 1 unit cell, 2 unit cells, or 3 unit cells thick of ferromagnetic calcium manganite at the interface, you either see blue above red, no real difference, and red above blue. And so we can then sort of tell the difference between these cases, and you do a few measurements, you analyze them all, and you end up with the conclusion that you have just a single atomic monolayer of ferromagnetism at the interface. So why might this be happening? Fortunately for us, we have a really nice roadmap from Nanda et al., who performed density functional theory calculations on this system. And basically what you find is that your ruthenate loses some electrons and transfers them at the interface to the calcium manganite. And what this means is that we now have competing magnetic interactions at the interface. So normally you have a couple of manganese 4+ ions. This means 3 electrons in the T2G level, and antiferromagnetic superexchange happens. As soon as you get a small amount of charge transfer, you now also have a small contribution of ferromagnetic double exchange, but it's extremely weak. So instead of a strong double exchange interaction, you only transfer about 0.07 electrons per manganese at the interface. And this leads to competition between these two interactions and ends up compromising between the fully ferromagnetic and fully antiferromagnetic state, and you get a canted antiferromagnetism, which explains why we saturate at 1 Bohr magneton per interfacial manganese ion and not 3. Okay, so now we sort of have a picture of how this interface is working, and the question becomes, how do we control these sorts of emergent magnetic interfaces? And we'd like to try electric fields. And so we suspect that the mobile electron at the interface is very important in the sense that it was predicted that by changing the magnitude of the charge transfer, you can move from fully antiferromagnetic in the case of no charge transfer, to fully ferromagnetic in the case of, say, 0.2 electrons per manganese being transferred at the interface. Okay, so that means we have to move about 0.1 electrons per unit cell at the interface, and we want to know if we can actually control this leakage to that extent with electric fields. And to do that, we needed to build this structure. So, so we grew gold on top of, as an electrode on top of calcium ruthenate, calcium manganite, a strontium titanate substrate, and then a silver back electrode. Now, the reason that we're gating through our strontium titanate substrate, as I'm pretty sure many of you have experienced, you really don't want to be pinholing right through your sample. Now, normally, when people are trying to do these kinds of measurements, what they'll do is pattern an extremely small, like nanopillar, and avoid pinholing through that way. Unfortunately, although neutron reflectometry is extremely sensitive, it's also always signal limited, and our signal scales basically linearly with our surface area, which means that we need to measure a big sample. My ideal sample is about something like this, but maybe 6-inch wafer, but you know, if we are super interested in something, we can make like a 5 by 5 millimeter sample work. But we usually ask for more. Anyway, so we backgate to avoid pinholing, and here we're kind of cheating because strontium titanate, as I'm sure you're well aware, has a very, very large dielectric constant as you cool down to 20 Kelvin or so, maybe 5 Kelvin, gets even higher. And that means that we can move a lot of charges with not that large an electric field. So in fact, Harold Huang's group at Stanford showed in the lanthanum luminate lanthanum titanate system that by backgating a strontium titanate substrate, you could move about the number of charges that we need within plus or minus a couple of 100 volts. So it really seems like we should be able to do this. The other problem that we run into is that we're looking at a ridiculously tiny signal. So if you remember the thickness of the ferromagnetic layer I mentioned earlier, we're talking about measuring, with polarized neutron reflectometry, a single atomic monolayer of ferromagnetism. So in order to do this, we really need something very, very sensitive, like polarized neutron reflectometry. So what we're going to do is we're going to heat our sample to above the Néel temperature. We're going to cool to 10 Kelvin in our desired electronic and magnetic field. And we're going to measure our spin up and spin down cross sections, and then we're going to heat up and repeat this for the next electric field. As I mentioned before, we're going to be highlighting the spin asymmetry, which sort of helps you to see the magnetic contributions of this to the scattering. In this case, we're quite lucky that the spin asymmetry ends up being pretty much linearly related to the magnetization at the interface. So larger spin asymmetry equals larger magnetization. So prepare to be underwhelmed here by our first measurement we ever tried on this. This is our 0-volt case spin asymmetry, and you will see that our error bars are large and we do not see much of anything. On the other hand, if you look at a minus 300-volt bias measurement and you sort of squint really hard for a while, you can convince yourself that maybe you see an oscillation right here. And if you look at the black line, which is a guide to the eye, it's also exactly the signal we expect from our sample if we have 2.5 Bohr magnetons per manganese at the interface. So this black line here represents a 2.5-fold increase in your interfacial magnetization. So this is not compelling, but it's suggestive that maybe we're on the right track here. So whenever we run into these sorts of signal problems, the way we solve these as neutron scatterers is we count for even longer, and usually we focus on a smaller range of reciprocal lattice vectors. So we do this again, and it starts to become a little bit more convincing. Here, we have the 0-volt case, again, where you can kind of see an oscillation now a little more clearly. This blue line is a fit to the data representing 0.8 Bohr magnetons per manganese. And this red case, at minus 400 volts, we amped up the voltage about as much as our safety people would let us. You have a red line which is fit to 2.6 Bohr magnetons per manganese. So it actually matches our first measurement really well, and the oscillation is a little bit more compelling. And if we look at just the very lowest Q data here, you see that the spin asymmetry of the red, which is minus 400 volts, always beats the spin asymmetry of the blue at 0 volts. So this is becoming more and more convincing. We do this one more time. Here I'll note that the cooling and measurement sequence is a little different. Instead of heating up in between every voltage state, we cooled and then at constant temperature measured at minus 400, 0, and plus 350. And now we're focusing just on the full width half max of this peak here to get the most counts per unit time. And you can see minus 400 beats plus 350. And if you integrate the spin asymmetry, you see that it becomes large at large negative voltages and smaller at large positive voltages. So hopefully I've sort of convinced you here that it is in fact possible to use neutron reflectometry to see really, really tiny electric field induced changes in your saturation magnetization in these sorts of interfaces. So the really nice thing about that first measurement is that we could assume that there were no structural changes whatsoever in our film with the application of an electric field. And we did test measurements, and this really seemed to be the case. Now, when we've done this sort of measurement on, say, ferroelectric systems, we often find that when you apply a field to your ferroelectric substrate or to your ferroelectric film, you get a change in the interfacial roughness or a change in the surface. And so it's important that we be able to detect this sort of effect not just when we have a very constant structure, but also when the structure may be changing. And I can show you now a really good example of that kind of a system when we look at metal oxide interfaces. So here, this work was inspired by work done by the Beach group at MIT and by the Wang group at Arizona University, where they were looking at voltage-driven oxygen migration between gadolinium oxide and cobalt thin film heterostructures. So the system they looked at was pretty much like this. They have a gold contact, some gadolinium oxide, an ultra thin cobalt layer, 9 angstroms or so, and platinum underlayer as an electrode. So you start out, and your cobalt film has in-plane magnetic anisotropy. You apply a voltage that pushes some oxygen from the gadolinium oxide into your cobalt at the interface. that changes your anisotropy so that it's pointing out of plane. You can reverse the voltage, drive the oxygen back out of the interface into the gadolinium again, and you recover your in-plane anisotropy. Or alternatively, you can just keep going with the initial voltage, totally oxidize your film, and remove the magnetization completely. So we thought this was a really interesting study, but there are a lot of unanswered questions. So how important is the gadolinium oxide? Can we substitute this with alternative materials? Can we do this with thicker cobalt, or is it a purely interfacial effect? If we use thicker cobalt, is it fully reversible still? And a variety of other sorts of questions. What is the real microstructural theory that lets us explain this kind of behavior? And so the way we decided to try and answer it is by doing polarized neutron reflectometry on something of a different stack. So here you have a palladium electrode, cobalt on top, it's quite a bit thicker. Gadolinium right below it, it's quite a bit thinner. And then you have a huge micron-thick alumina layer, which you can probably guess, since we need huge samples, we grow really, really thick alumina to make sure that we're not pinholing right through our sample. This worked sort of well. I'll admit that we had about a 70% sample fatality rate in these experiments, but for the most part, the ones that worked pretty well. So what we're hoping to do is see if we can get this alumina to act as essentially an infinite oxygen reservoir that will then move through the gadolinium oxide, which sort of acts as a catalyst instead of the oxygen supply, into the cobalt, and then whether it's reversible all the way through the 15 nanometers. So we performed polarized neutron reflectometry on this sample after electric and thermal treatments at 230 degrees Celsius at plus or minus 40 volts. And we're going to try to understand the length scales of reversibility, understand how the treatment affects film quality, and map out the oxygen migration in these samples. So here are the results from our first as-grown sample. You see the fit looks pretty darn good. And what we end up with is basically what we were hoping for from the design structure. So you can see the alumina layer is really thick, thin gadolinium, really low scattering length density in the cobalt here. That's the solid line, and it's exactly what we expect. And then a palladium capping layer. And then here the dashed line is the really strong magnetization within the cobalt. Okay, so we do our first plus 40 volt heat and electric field treatment, and you see that the scattering length density profile of your cobalt layer changes quite a bit. It increases a lot, and your magnetization decreases, especially here at the interface. So what this is a signature of is the transport of oxygen from your alumina and gadolinium oxide into the cobalt, which then suppresses the magnetization. So that's basically what we expected. Things start to get a little bit more surprising when we reverse the voltage, and we see that the magnetization, this blue dashed line here, recovers most of the way. Especially it recovers a lot at the interface, and less so far away from the interface near the bulk of the film. In addition, excuse me, in addition, most of the change in your nuclear scattering length density, this solid blue line, it recovers a little bit, but not a ton, at the interface here, again, and not at all farther away into the bulk of the film. So what this is suggesting is that we have a quasi-reversibility with electric field of the oxygen migration. So we were very worried when we did these measurements that we were going to be confusing the effects of the electric field with the effects of thermal conditioning. We wanted to apply the heat treatment at the same time because that's how all of the previous studies had done this. But anytime you're heating up a bunch of metal nanostructures, there's possibilities for interdiffusion, oxygen migration that's just thermally induced, and other effects like that. So what we wanted to do is grow the same sample, and then subject it to the same treatment, but without electric fields. And so what we end up seeing is that, yes, our scattering length density increases quite a bit when we do the heat treatment, but saturates quite quickly, and you don't move nearly as much oxygen into the cobalt layer. And in addition, you don't observe nearly the same degree of magnetization suppression. So this is suggestive, that most of the effect is in fact electric field driven and not thermally driven. So we can actually see that especially well if we look at an oxygen mapping. So the solid dots here are the oxygen content in the cobalt layer after our plus 40 volt treatment as opposed to the initial thermal treatment. So you can see we've moved far less oxygen in this case. And then we look at the second treatment here, where we use a minus 40 volt reverse treatment. You see we lose a lot of oxygen near the interface, and the second thermal treatment does basically nothing. So we lose a lot of oxygen here at the interface, and it stays basically the same throughout the bulk of the film. So what this tells us is that the electric field forces way more oxygen than the thermal treatment, and it quasi-reversibly, but not entirely reversibly, drives it back into the oxide underlayers. And you can really sort of see that here where I've plotted both depth profiles for comparison. So what this is telling us is that the electric field effects seem to be largely interfacial within the bottom 5 to 10 nanometers of the cobalt, and that the thermal treatment is making a small change to the bulk of the sample. So in order to really sort of come up with a microstructural model for this behavior, we attempted to do X-ray absorption spectroscopy, which gives us element-specific information about the magnetization and the oxygen. So you can see here the cobalt L edge for the as-grown and for the electric and thermally treated sample. And you see that we get an extra oxidation peak in the cobalt after the treatment, just like we expect. And you also see that we have a suppression of the cobalt magnetization, just as we expect. What's really surprising is that the gadolinium oxidation state is unchanged here. You see no real difference in the before and after states, before and after the electric field treatment in terms of the gadolinium X-ray absorption spectra. And so this tells us that the gadolinium is acting, as we were hoping, as a catalyst and not as an actual oxygen donor. The final piece of the puzzle here came when we do magnetometry on this sample, which if you look here, the black line is the as-grown sample, the red one is the electrically treated sample, and you see that initially we have a single magnetic phase here, whereas after the treatment we have a single hysteretic phase and a large reversible component to the hysteresis. And so this tells us that through our electric and thermal treatments, we've moved from a single-phase system, a single-phase magnetic system, to a two-phase magnetic system. And this is what we think is really going on here. So if you look at this is the microstructural model that we come up with based on all of this. And so what we think is happening is you see, you have all of these grain boundaries in your system. So backing up a little bit, all of these samples were grown through low or room temperature sputtering. And this means that we have basically super low quality films. And in fact, the Beach Group, when they originally did these studies, showed that the lower quality your system, probably the stronger this effect is going to be. In their highest quality samples, they didn't really see much of anything. It just didn't work. So what we think this means is that oxygen at the grain boundaries in these metallic structures is very highly mobile. But away from the grain boundaries in the bulk of these grains, not so much. So here I'm plotting the dark blue here is oxidized cobalt, and the light blue is not oxidized. It's just pure cobalt metal. So we think we apply a voltage, and our oxygen starts to leak into the cobalt here, starting in the alumina and then passing through the gadolinium as a catalyst, and then starts oxidizing the cobalt nanograins from the outside in. But then when you reverse your bias voltage, it does not actually reverse in the same way. You start to pull the oxygen out of the cobalt at the interface, at the edge of the grain boundaries, but as soon as you remove the cobalt oxide from the grain boundary, you suddenly regain the metallic conducting nature of these cobalt nanoscale grains, and you now screen out all of your electric field from the interior cobalt oxide. And so you end up with cobalt metal on the outside, cobalt metal on the very interior, but in the center, or sort of in between those two layers, you have oxidized cobalt that gets trapped in these grains. And so this explains why we have gone from a single-phase system to a two-phase system. So in summary, hopefully I've convinced you that we can control these sorts of functional interfaces through a lot of different routes, whether it's charge transfer, oxygen migration, or hopefully integration with ferroelectric layers, and that polarized neutron reflectometry is a really powerful tool for looking at these kind of heterostructures. As a scientist at a user facility, I always sort of end with a plug that if you're interested in looking at, I guess in this case it would be a ferroelectric, magnetoelectric heterostructure, and you think neutron reflectometry could help you, shoot me an email or talk to me sometime after this session. Thank you. Any questions?
Okay, well, all the questions have been thought of. Could you comment on the robustness of the fitting procedure?
Yeah, so the fitting procedure is usually very complex. So you often end up with multiple solutions to the data. Since we can't go out, it's essentially taking a Fourier transform of your structure, right? And we can't go out to infinite Q. So one of the big things we spend our time on is figuring out what explicit sort of parameters we're sensitive to and how we can, and what exactly we can and cannot say. So in this case, one of the big sort of comparisons we made is fitting the sample with constant magnetic structure and without, and showing that specific models just don't work. That's actually what we spend a lot of our time on.
When you say they don't work, what is the criterion for it?
So we use just pure counting statistics in terms of what is the chi-squared of the fit as opposed to given our error bars, and we do a lot of model optimization using I'm blanking using Monte Carlo methods.
Any questions? Oh.
So we haven't in this case because these measurements take on order 18 hours or 20 hours, and neutron time is about, I don't know, $10,000 a day. So other groups have. So the Beach group has gotten up to, I think, a couple hundred cycles. I don't think they see a ton of degradation at that level, but in terms of like tens of thousands of cycles, I don't think anybody's gotten there yet. I could be wrong.
Any other questions? If not, let's thank Alex again. Thank you. Our final speaker of the session is Alessio Morelli from Queen's University of Belfast, who's going to tell us about polarization switching in bismuth-ferrite nanoislands.
I need just the pointer. Yeah.
Let's see. Yes.
Yeah, and okay.
You can plug this thing in. If your PC is fast enough, it will recognize it. It should be okay to try it.
Let's try.
No?
Yeah.
Oh,
Perfect. Okay. Good afternoon, everybody. 5 minutes before the end, you. Okay. Good afternoon. I'm Alessio Morelli from Queen's University of Belfast. I first of all thank the organizer to give me the chance to show my results here, and I will show you that I can I can switch deterministically the polarization variant, not only the domain organization, but the polarization variant in bismuth-ferrite nanoislands. So first of all, why I'm doing this is because memories based on current controlled memories, they have a serious problem deriving from overheating, deriving from Joule effect, because there are the currents. Therefore, solutions have been thought during the years, and one of the possible solutions is to use for memory bits magnetoelectric multiferroic materials, by which since I use electric field to switch the magnetization, I would have no heating because I don't use currents, and I would have a fast write procedure typical of the ferroelectric memories, and a non-destructive read procedure typical of the magnetic memories. Therefore, in this way, many systems have been studied, intrinsic multiferroics, but most of them, they are low temperature. Room temperature are most promising are multiferroic heterostructures, and quite successful have been a multiferroic heterostructures based on bismuth ferrite. Bismuth ferrite actually is a multiferroic in itself. It has a ferroelectric polarization. Uh-oh, it's gone. Okay, with a rhomboedral structure and 8 possible polarization variants. And the interesting thing is that it is antiferromagnetic as well, with the antiferromagnetic planes here displayed in yellow, lying orthogonal to the polarization variant. And this is the internal coupling in the bismuth ferrite, internal magnetoelectric coupling. If now we use in multiferroic heterostructure a ferromagnet deposited on top of the bismuth ferrite grown on the 001 direction, we can have, as you see from the top view, we have, under certain conditions, the magnetization of the top layer aligning together with the antiferromagnetic planes, with the projection of the antiferromagnetic planes. Therefore, being a ferroelectric bismuth ferrite, we can imagine that it has been shown that by switching by electric field the polarization, we have a rotation of the antiferromagnetic plane, and therefore the overlying magnetization rotates, which then gives us electric field-driven magnetization control. But the point here is that when you do electric field switching in a 001 bismuth ferrite structure, you can select the autoplane component, and then you have 4 variants available, and therefore you can end up in any of the 4 variants, included, as you see, variants for which the polarization switching gives an antiferromagnetic plane whose projection on the surface gives no rotation on the magnetization. Therefore, we need to achieve it was recognized that it is definitely needed to get the deterministic switching. Therefore, meaning that we needed to be able, by applying an electric field, to select the variant that we want. Therefore, studies have been done, and the first success was this one, but the point was that in plane electrodes were used, and therefore, if we think about devices, you can understand that we need a perpendicular geometry. Therefore, studies have been done to achieve deterministic control of the ferroelectric switching in bismuth ferrite by using an autoplane electric field. And it was found out here by Balke and collaborators that using an SPM probe, an atomic force microscope with the probe, a conductive probe, and using this as a movable top electrode, we can select the polarization variants, in this case, as you see by the schematics, by the movement of the probe while we apply the electric field to switch the autoplane polarization. Furthermore, it has been shown that if you do this procedure in a continuous film, then you have to respect the boundary conditions from the surrounding material. Therefore, if you have if it is ferroelastically, if it is unfavorable, then you have a relaxation, as you see on the top plot. While if you do the same experiment on an island, obviously there is no boundary conditions, and so you have no relaxation. And finally, very recent result, it was shown that on the full structures, bismuth ferrite, cobalt iron, and top electrode, by an autoplane electric field, it was possible to switch the magnetization even by 180 degrees. But the thing here is that all of these structures were mesoscopic structures. In the range, in the best case, they were 2 microns by 8, 3 microns by 3, in first place. And while we need to go to the nanoscale to consider utilization in memories, and so this has to be verified in nanoscale structures. And especially in this last result, we have a multi-domain structure, both on the bottom bismuth ferrite in the switching of the polarization domains, and on the overlying cobalt iron, which gives me a very low net signal, because the signals cancel each other from each domain to the other in the full structure. Therefore, the idea is to go downscaling in lateral size and having actually the same structure basically, with the bottom electrode, bismuth-ferrite, ferromagnet, and do the same on the, in this structure, but switching the magnetization by electric field. This would bring us towards nanoscale, perpendicular geometry, low right voltage, and finally will give us the possibility to have a monodomain structure. Monodomain final configuration, sorry. This is what I want to show you. First of all, deterministic switching is needed. Is needed to be shown that it's possible to select which variant you want and have a monodomain bit, let's say. And here is how I fabricated the islands. I will show you. I use a stencil mask on a thin film of bismuth ferrite, the blue layer, over a bottom electrode. Evaporate aluminium, which will be my sacrificial layer. Removal of the mask gives me an array of aluminium dots, which then allow me to go and fabricate nano islands with the low energy of the ion beam, so that I can achieve little ion implantation, which otherwise will destroy the functional properties of my material, and will allow me to have anyway nano islands, despite the low energy, which broadens the beam and so lowers the resolution of nano fabrication. While having the sacrificial layer in islands will nanostructure by itself the film. Removal of the by chemical etching of the aluminium will lead me to have nano islands of bismuth ferrite. So here is my sample. Already you can see the fabricated area. Here is the corner. I fabricated a 5 by 5 micron square structure. And here you see one corner with the islands and part of the film. If we see the characteristics of the island, they are between 20 and 30 nanometers in height and 400 nanometers in diameter. While by the masks I have, I can go down even to 250 nanometers, which is another thing I will have to check. And if we check by piezo response for microscopy, the polarization domain configuration, we can see by the vertical signal here, we have a preferable, favorable downward polarization pointing towards the bottom electrode. And the lateral PFM phase show me that I have in the two different directions to reconstruct the 8 possible variants. I can see that I have a stripe-like domain configuration. You can see on the top right corner of in the original film. And the fact that it is a stripe-like configuration in the original film yields that if I magnify this area, which is corresponding to the island, that I have, most of the times, I have multi-domain configuration in the island. Finally, I can check the functional properties. I see that between island and film, they're both obviously, the film is obviously ferroelectric. The island still retains ferroelectricity. And there is only a slight change in imprint due to a bit of ion implantation. Now, on these islands, I want to show you that I can control the polarization variant. How? First of all, by applying the autoplane field, I can select only 4. I cannot select between the 4 variants because they are basically energetically equivalent. And the same it happens even without electrode. If I use as top electrode an AFM tip, here I can directly select the autoplane component of the polarization, but not particularly the variant. But in this case, it has been shown by other researchers that the PFM, the AFM probe generates an inhomogeneous electric field with a radial component in plane, which is symmetric. Therefore, we don't break the symmetry yet. But if while applying a bias, we scan in a certain direction the AFM probe, we can generate a so-called trailing field, which actually, because we break the symmetry of this radial field. And finally, this trailing field would actually allow me to deterministically select the polarization variant that I want to select. So this is in theory. Let's see what happens in reality. I have the island scanning with this particular direction, -1, -1, 0. And here is the vertical piezo response force microscopy. Shows me that I selected one of the 4 variants on top, pointing upwards. And now I would expect a selection of one of the variants, but it's not what it happens, because if I superimpose the topography, a mask of the topography, I see that it's multi-domain still. And if I analyze it, I can see that it's a kind of quadrant multi-domain configuration, which is interesting in itself, but it's not what I want to achieve now. But not all is lost. I will call this reset operation, because I will need it. And let's see what happens by reverting the polarization back to the downwards direction. So this time I apply a negative bias from the bottom electrode, and I see that first of all, I can actually select, invert the autoplane configuration, the autoplane component, and if I reconstruct from the 2 lateral PFM phase images, I can see that I get a monodomain island with only 1 variant, and actually the variant is the one I wanted to select, because the variant is opposite to the slow scan axis with which I was scanning while applying the bias, which is very good for me, is what I wanted to show. But most importantly, I can show that by passing through the reset operation, so now I apply positive bias, I get back to this quadrant configuration pointing upwards. I apply negative bias again, but this time in a different direction, 110, and I get actually another component, one of the other 4 variants, and so forth and so on, reset, different scanning direction, I get the exact variant I wanted to select, and finally the last variant available. So I can show you that in a with a 2-step procedure, I can select one of whichever of the 4 polarization variants I want in the island, and have the island all with this polarization variant, which therefore will allow, by producing, fabricating islands with covered with cobalt ferrite, will allow to have toggling of the, possibly, it has to be verified, toggling of the magnetization direction just by scanning over it and applying a bias. Now, do I have time enough? Fine. I will try to go fast. I have just 2 questions which I want to answer. So why, first of all, it works for polling downwards, not for polling upwards? And second, why I need actually always to pass for passing from one polarization variant to the other, I have always to pass to the by the reset operation. First of all, about why I cannot get the monodomain with positive polling, in my opinion, is because, as I see by the imprint, the favored variant is downwards, and as I see as well by the original domain configuration, which is mostly downwards, I see that there is an imperfect screening at the surface, and therefore it will need much more time for screening after polling upwards. Too much time, so that the monodomain configuration is unfavorable when I have upwards polarization. So this is my opinion. I'm open to discussion. And secondly, why I have to pass through the reset operation, why I cannot pass simply like this, but I have to reset and then go to the other step. Here I needed the help from simulations for the electric field, which shows me if I model the tip as a top electrode of 10 nanometers, and I have a film of 40 nanometers, applying the bias from the bottom electrode, -6 volts in this case, I see that I have high inhomogeneity at the edges of the contact area, okay, nothing special. I see that the inhomogeneity is for both normal and transverse component of the field, but now the interesting thing is that if I check the values for the 2 fields over this line very close to the surface, I see that here and here at the edges of the contact area, the magnitude of the in plane field is comparable to the magnitude of the field that I use, the autoplane field that I use to switch the autoplane polarization. Therefore, I would assume that even without switching the autoplane polarization, so if I have a pointing down and apply a bias which will not switch upwards but will point down the polarization, I still should be able, since this in plane field is strong enough, I still should be able to switch it as I want. Just by moving the top electrode in one side, I will tilt all the polarization in this direction. But it doesn't happen. And this is why, if I check better, and I see more through the depth, I can see that, yes, the autoplane, the blue here, the blue field, the autoplane field, which is the switching one, yes, it decreases through the thickness, but not as fast as the plane field at the edges. The plane field decreases already by 33%, and to much smaller values than the field which is in the middle of the electrode. Therefore, what I suppose is that I have in plane switching. I mean, the field here is strong enough to switch, but is limited to a volume very close to the surface. Therefore, if there is no autoplane switching, only this little volume switches, and then nothing else happens, and the rest of the film is still with the same variance, and so it back switches to the original situation. While if I'm already switching autoplane, the switching autoplane switching can choose any of the 4 variants, and which are almost nearly equivalent energetically. Therefore, the kick of this switching in this small volumes would be enough to direct all the rest of the variant in the rest of the volume. And with this, I can conclude. I showed you that we can produce nano islands smaller than 1 micron island, approaching the 100 nanometers in diameter islands of bismuth ferrite, retaining the ferroelectric properties, by which I was able to study the possibility of selecting a polarization variant at my will in a confined volume of the sample of the bismuth ferrite, which will be very interesting to study the same process in cobalt ferrite capped bismuth ferrite islands to see if it's actually possible to select the magnetization variant, or if the exchange bias, the exchange coupling, is based on something else and doesn't work with monodomain configurations. And with this, I thank you for your attention, and I leave you with acknowledgements.
Questions?
Did you try to change the external screening parameters of your sample, so by measuring in ultra vacuum or by changing the humidity to see if you have the same?
No, I didn't. That might help with switching upwards, I know, yeah. But I have no such control in my setup. Yeah.
Other questions?
Oh, good. Everything was clear then.
I wanted to ask you something about switching in such thin nanostructures. So the edges of the nanostructures are almost guaranteed to be very defective.
Yeah, yeah.
By milling.
They are for sure.
And so when you consider your model, you assume the disk on a semi-infinite dielectric plane.
Yeah.
Whereas,
I mean, yes.
Right. So what are the effects? Do you observe, let's say, from reproducibility between different islands, some significant edge effects?
Different islands tend to behave a bit different. This one was, I was very happy. It was only the second island I was trying, and it was successful. Another island didn't want to do anything, for instance, probably because I was too close to the edge of the structuring area, and that there were more. No, I was not very close. I was more close to the center, where I was digging more, and the ions were hitting more. Or simply because probably the sample itself, the parent film itself in that region was defected, and if you can avoid defects, this would work very well. Yeah, the point is that as well, the thing that I cannot have the upwards polarization selection can derive simply by the way the film was grown. And so it's trying with different kind of films. Purely stripe films might help, or monodomain films, okay, is asking too much, but if I can get my hands on them. Yeah.
Okay. Thank you.
Thank you.
Any other questions? Okay, if not, let's
Coffee.
thank the speakers again for the session. Now it's time for a coffee break. Yeah, so in this field modeling,
Yeah.
you have to be careful with infinite fields.
Yeah, I mean, the modeling my colleague did was on a,
So
it was something like 2 microns
it doesn't
long.
matter. So if you have a
Okay,
sharp
yeah.
edge and it's a FEM model, what saves you from an infinite field is discretization of the mesh. But in reality, the analytical model would give you an infinite field. And so they always tend to be extremely large at edges. It's sort of, yeah.
Mm-hmm.
And this is actually a conundrum the whole community of nanocapacitors
Okay.
for a while.
Yeah.
So there's no
Yeah.
good solutions for it yet, other than trick.
As well, the model is not completely perfect.
Are you chairing? Who is the chair?
I'm next.
Are you next? Are you the chair? Right, good.
I didn't have to do any special tricks to get it.
And this one was okay, but come on, already.
I'm not sure why they weren't using the microphone, but I'm more inclined to use the microphone.
Yeah. Are you chairing?
I'm chairing.
Okay. So I'll use it.
Hello. I'm gonna wire people up with a mic, I think.
I set it up a chain of command, but it doesn't get you any more money.
Yeah, that's VJ. He's after me, I think. No. After Oswaldo. Oswaldo's after. Yeah, sure. I'm just, yeah, actually you go first because I'm going to be here anyway. So. 4 tops?
I'm not chairing.
Are you after this?
Very, very end.
Oh, okay.
I thought I was chairing now.
Would have been logical. I will. Okay, fine. Yeah.
While if you which very probably so, but still add information, and then there are, so if I have to apply a higher electric field, I can show you applying higher electric field. Yeah, this, but if I have to apply higher no, sorry. Higher voltage. Now I the four is the only one. Last one, but the others are not passing several times. Because especially at the beginning I was trying to apply it. Then I saw that doesn't matter what to do. Some of it. But every time then go up. So after going down, it was coming out the one.
Okay, good afternoon, everyone. Welcome back to the second session here. My name is Zhou Guangye from Simon Fraser University, Canada, and I'm also one of the co-organizers of the symposium. We have 4 papers for this focus section on lead-free piezoelectric, or lead-free oxide perovskite. And our first speaker is Valentino Koop from Oak Ridge National Lab. He's going to talk about designing high-response lead-free piezoelectrics. Valentino?
Thank you, Xiaoguan. Before I begin, I just want to thank the organizers for inviting me to present my research here today. Attending this conference is always a bit of a pleasure for me because, this is the first workshop that I ever attended as a graduate student. And so when I come back, it's always nice to, see what's going on in the field and to visit with old friends and meet some new people. So today, I'm going to discuss our efforts to use density functional theory to try to design and discover high-response lead-free piezoelectrics. And so our approach to this is really what I refer to here as this prediction to synthesis triangle. So we know from first principles what's typically done is we can take our electronic structure calculations, we can use chemical design concepts, and nowadays people are using high-throughput calculations in order to look at a number of different chemical compositions, structures, and try to find things with enhanced properties. So here, if we're looking for piezoelectrics, we try to find things with enhanced D33 coefficients. And then you take that structure that you think is the best structure, you hand it off to your experimental colleague, and you say, hey, why don't you go and try to make this? Now, what tends to happen a lot of times is, we as theorists, we tend to predict things that just can't be made. And in fact, this was one of the things that I got out of coming to this workshop was I spoke to an experimentalist, and they went, you guys are crazy. Those things just can't be made. And they always had like a list of reasons why you couldn't make a certain compound. And so the third pillar here is really that we need to start looking at things like phase stability. If we're looking at a solid solution of a material, we need to understand how these two end-members compounds go together. Do they want to form a solid solution, or do they want to phase segregate? Or do they want to form other forms, like, for example, if instead of forming a perovskite, you form a Aurelia structure, or even you form some sort of binary oxide instead. The other thing that's important is, especially in the field of ferroelectrics, is to understand things like transition temperatures. If we want to make a device out of a material, let's say ferroelectric, we need to have some kind of polarization within the material. We know there's a transition temperature, and if that transition temperature is too low, then that thing would not be useful in whatever application you're thinking about. So ultimately, we want to be able, as computational scientists, to predict materials that have enhanced properties that can be synthesized and remain active under device-relevant conditions. And of course, this really requires us to have a strong dialogue between theory and experiment. And so what I want to do today is sort of show you some of these excerpts of these dialogues that we've been having. And the first is looking at this ternary solid solution. Here we're looking for things that, maybe trying to discover a lead-free, high-response piezoelectric. And then the second thing that I want to talk about actually starts from experiment. And we want to understand basically strain-induced phase transitions in bismuth ferrite thin films that lead to enhanced piezoelectric responses in these thin films. So this is just a quick note about our computational methods. So it's all density functional theory. We're using LDA, and in some cases, LDA plus U. Usually, we're looking at 40-atom unit cells. For the bismuth zinc titanate-based systems, we looked at a number of different cation orderings, and we also looked at things with the special quasi-random approach. And this was so that we can try to mimic disorder within these materials. One thing that we found is really A-site ordering was not important, but the B-site showed a strong tendency towards rock salt ordering. So most of the things I will show you today will actually be things that have rock salt ordering. And this comes out of size and charge mismatch between zinc and titanium. For bismuth ferrite, they're just going to be 2x2x2 orthogonal supercells that we considered. Okay, so the first thing looking at this ternary solid solution. So when we want to discover new high-response piezoelectrics, where do we start? Well, one idea, let's say if we're ignoring relaxers, we start with thinking about something like PZT. So this is our prototypical high-response piezoelectric. So we know that it's a solid solution of lead titanate and lead zirconate. Lead titanate is that prototypical ferroelectric. It has a single phase transition as we go from cubic to tetragonal. Lead zirconate, on the other hand, is antiferroelectric, but if you put a little bit of lead titanate in, it starts moving into this rhombohedral region.
And right at the boundary between this rhombohedral phase and the tetragonal phase, we have what we refer to as a morphotropic phase boundary. For a little while, people didn't know what was here, but you needed to have something that mediated the change from tetragonal to rhombohedral, and it turns out this is a monoclinic phase, and this is really where we get these high responses. You have this monoclinic phase that really mediates with a little bit of electric field. You can go from two materials with two very different structures, and that's what gives us this high response. So the question is, so one thing that we can do is we can search for things with these morphotropic phase boundaries. And so what we like to do is start with something on this end that's antiferroelectric or rhombohedral and move over here to something like lead that's tetragonal. So one idea we had was to start with something like lanthanum zinc titanate and bismuth zinc titanate. And this is sort of an easy system for us to measure, well, at least to compute, because we only have to worry about A-site cation mixing. This one here is an antiferroelectric. This one is a tetragonal thing, and it has a very large C/A ratio. And it was actually discovered with lead titanate and found that it had a much larger polarization than lead titanate. So we started off, we looked at that solid solution. And so this is here sort of a phase diagram. This is the polarization as a function of percent bismuth zinc titanate. And what you can see are two things. First of all, if you look at this end here, we get these very low polarizations. And the reason why this is not favorable is actually Ilya and Andrew did some nice work where they showed that there's a sort of linear relationship between the polarization squared and the transition temperature. So these low polarizations sort of imply that you will have low transition temperatures. On this end here, we have this very large polarization. And when you have polarizations this large, it's often questionable as to whether or not this thing would be ferroelectric. So can we actually switch this compound? Another thing that came about, talking actually to Zhao Guang at the Ferroelectrics workshop at Iowa State, he mentioned that if you try to put a little bit of bismuth into a lanthanum, it's very hard to get this thing to mix. If you try to do the same on this end, it's hard to get a little bit of lanthanum into bismuth zinc titanate. And so this would be hard to actually grow. But he suggested that perhaps we can improve solubility and improve this high polarization if we add some lead titanate into the mixture. And so we decided to look at this phase diagram. So here again, if we look at this, we have this one side where we have a rhombohedral or antiferrodistorted phase. We have this high polarization phase. So perhaps if we start mixing these things together, in here we'll find this monoclinic phase that might be useful for synthesis. So of course, the first thing we do is we just look at the properties of these materials. This is the polarization as a function, for this ternary phase diagram. So over here with the lanthanum zinc titanate, we get these very low polarizations. Bismuth zinc titanate rich compounds have very high polarizations. And we kind of block off this region. And these are basically going from polarizations roughly the size of lead titanate to something about 1 coulomb per meter squared. Then once we have this, we can look at the direction of the polarization. And so this is just the polarization dotted into 001. So this gives us the red regions now are the tetragonal regions. If we dot it into 111, these red regions are rhombohedral. And then right in between here, we find that we get some monoclinic phases. The key here to why we get this rotation of polarization from here as we go towards these lanthanum-rich compounds, it really has to do with lanthanum. What we find is that lanthanum is this large, heavy ion, and it's kind of sitting in these A sites. And when ions displace towards it, they want to actually avoid lanthanum. And so they tend to displace in different directions. And as you increase the amount of lanthanum, then you really get this rotation from 001 all the way to this 111 direction. And this is exactly what we see in lead zirconate titanate, right? In that case, zirconium is the big ion that's causing things to move around it on the B site. Okay, so so we were able to map that out. And then the next question is, what about things like phase stability? What about the transition temperature? As I said before, Ilya and Andrew did some work on bismuth-based compounds and lead-based compounds. And what they did was they just computed the polarization using density functional theory, and then they compared it to the transition temperature that you get right out of experiment. And you can see that you get this nice linear agreement. You get a slightly different prefactor here for bismuth-based compounds than lead-based compounds. Nevertheless, we decided to use this prefactor, the one they had for the bismuth-based systems in our study. And so these are just our results. They're just kind of lined right up with what Ilya says. There's particularly they're lined right up with these bismuth-based compounds, which is expected. And then we can go and map out this whole region, and we can see that we have this huge region of blue where we have these very low transition temperatures. And we can sort of say that this region are the ones with the most useful transition temperatures. And again, this is really due to the lanthanum, right? We plot this as a function of lanthanum zinc titanate concentration, and you can see very clearly that for large concentrations of lanthanum zinc titanate, you have, here we have no polarization, and then as we increase up to this line here marks basically where room temperature is. And then once you get over this room temperature, we think that these are the regions where that might be favorable for device applications. I point out that this is a log scale, so it looks much more dramatic than it looks there. Okay, but the final question is, can it be made? Remember, we started off with something that we thought it was a nice system to look at, but it turns out that they might have some solubility issues. And so, of course, what you need to do is evaluate the Gibbs free energy. We can get this enthalpy of formation directly from our DFT calculations. And then for entropy, we just use a simple ideal mixing model. So this is the entropy of mixing. And this is typically what people do in the metal alloys community. So just how this works, if we have delta G as a function of percent BCT, this black line here is just your enthalpy of formation. And then as we increase the amount of entropy, essentially, we see that we get regions where this thing becomes lower than, delta G is less than 0. So here, to understand, the phase stability of these materials, what we do is we just find where delta G equals 0. That's where we should not have, the KT where you shouldn't have, where the solid solution should be more stable. And so we can plot that on a line here. And so, if I mark off again, room temperature, you can see that you get regions here that should be stable and regions over here that should be stable. This is just the PZT-BT mixture. This actually agrees quite nicely with what people found for bismuth, manganese, titanium, bismuth, zinc, titanium, lead titanate solid solution. So for the BZT-PT line on that ternary phase diagram. So, we can then do this whole map again for our ternary solid solution. And this is the line I showed before. But now you see we have two regions of relatively nice phase stability. So we have this region right around lead titanate. And then we have this band here. And surprisingly, we found something right in the middle with 50-50 BZT, LZT that seems that it might be promising. And so a colleague of mine actually had a summer student, and he was looking for something for that summer student to do. And so he decided to pick up this 50-50 BZT LZD compound. And this is the sort of XRD from some of their work, and you can see that you've mostly got perovskite peaks. There are a little bit of impurity peaks, but it's mostly a solid solution of bismuth zinc titanate, lanthanum zinc titanate. So this seems like very promising. He thinks that if you refine this a little bit more, you can get rid of some of these impurity peaks. But the problem, this was not a very favorable compound in the first place, so we kind of abandoned that endeavor. So anyway, we can put these together. You can look at the direction of the polarization. We can map out sort of where the most useful TC regions are. We can predict phase stability. And then, the sum total is we can say, okay, this looks like a favorable region to actually start looking at. So here, we're trying to get people to actually go in and look at this right now. Now, one thing that I saw recently was a paper that actually looked at the phase diagram, the piezoelectric response along this line. So, this is sort of in our region of phase stability, but we didn't think that the polarizations would be so high, the response would be so high here. So what you can see is this region here really corresponds to the strongly tetragonal region. And then as we go from here up, you see that we're getting this increase in piezoelectric coefficient. And this is really the region that we think that is actually going towards this monoclinic region in our calculations. And so it sort of seems that we're on the right track in these predictions. Now, I just showed you a whole bunch of things with lead in them, and I said that we're really interested in looking for lead-free compounds. So we have one idea that perhaps we can use strontium as a replacement for lead in these materials. And that idea comes out of some previous work that we did on bismuth, strontium, zinc, niobate. And we did a comparison of this compound with a lead-containing one, bismuth, lead, zinc, niobate. And we computed the polarization in both compounds. And what we found is for the strontium-containing compound, we had something about 79 microcoulombs per centimeter squared. But then if we moved over to the lead-based compound, we see that we don't get that much of an enhancement in the polarization. And this is very surprising, given the fact that we know lead has these lone pairs that are thought to enhance polarization within this material. But we think that really, when we start to put strontium in these high polarization environments, that we get large offsetterings of strontium. And we think it's more related to if you think about something like strontium titanate, it has this very flat potential energy well. And so, when you have something that's very polar, then it can push that strontium off the off-center positions. And we think that's kind of related to what's going on in here. So anyway, we can take that, we can substitute now strontium titanate within this material. We can go ahead and map out polarization directions. We can find out where these monoclinic regions are. We can then, look at predicted TCs and stability. And so we think that this triangle here is really where we think someone should start to look. These aren't experimentally verified yet, but we're hoping that perhaps the next time, I'm at the Ferroelectrics conference, that we'll have some results that show that, indeed, you can have these high piezoelectric responses in these materials. Okay, so I talked a lot there about how we can use chemistry, so chemical compositions, to look for this morphotropic phase boundary. But another idea is, of course, we can look at strain to try to move our material from a rhombohedral phase to a tetragonal phase. So one thing that people looked at is bismuth ferrite. So bismuth ferrite in its ground state is rhombohedral. But if you do it by thin film synthesis, you can actually increase the compressive strain, and you get a region over here that's tetragonal. It's not completely tetragonal. There's a slight monoclinic distortion, but nevertheless, it has a large C/A ratio, and people refer to it as a tetragonal-like phase. So it's always called a T-prime phase. So the question is, what goes on right here, right? Can we find this morphotropic phase boundary or monoclinic phase within this area? It turns out when you grow these things on lanthanum aluminum oxide, what you get is really a coexisting region. So you get something where you have a T-prime phase, and it's always mixed with this S-prime phase. Now, I'll point out, you can get pure T-prime phases in these structures. You can never get pure S-prime phases. It only exists when you have this sort of stripe phase. Two things that happen when you do this. First of all, if you just had the T-prime phase and you tried to switch these, you actually can't switch them. There's no, it's very difficult to switch. But if you now have this S-prime phase, you can get nice piezo response. And this is sort of a micrograph showing how you can switch this phase. The next thing that happens is, in fact, in this striped region, you get a large enhancement in the piezoelectric coefficients. And so the question are, what are the structural features that give rise to this enhanced piezo response? And that's what we wanted to understand. But to do that, we need to know what this S-prime phase looks like. So, the T-prime and R-prime phases, they exist by themselves. You can characterize them pretty well. The S-prime phase only exists in this stripe structure, and it's a thin film, and it actually is quite difficult to deal with. But our experimental colleagues were able to extract some information from this. So they did some XRD on these thin films, and they got the A, B, and C lattice parameters, as well as the angle. So you have alpha, beta, and gamma. And so for our Ferns principles calculations, we fixed B over A and C over A, alpha, beta, and gamma, and then we optimize the A lattice constant. And so this is what we have of the energy as a function of the A lattice parameter. And the first thing you can see is that this S-prime phase is much higher in energy than the R-prime phase, but it's very close to this T-prime phase. We can go further and look more at the structure, and you can see, lattice parameters is really just in the middle of the R-prime and T-prime phase. But if you look at this T-prime phase, one thing happens is that once you start this epitaxial strain, you shut off the rotations around the C-axis. But in the S-prime phase, even though it's very close in energy here, you still have these C-axis rotations. And so, you've got something where you're intermediate structurally between these two phases. You're energetically close to this, but you look more like this R-prime phase. And I think because you had these rotations for a long time, this S-prime phase was actually referred to as another type of R-prime phase. Okay, so the piezo response. So here I have just the D33 for these different phases. So you have the R phase, and you see you have a relatively large piezo response relatively to the other compounds, relative to T, which is very small. But in the coexisting phase region, we get this high response. And so we were questioning, okay, what gives rise to this response? And so we basically computed the E33 coefficients for these three phases. And surprisingly, we didn't find an enhancement in this S-prime phase alone. So the key then must be sort of this coexisting between this S and T prime phases. Now, that is something we're not going to look at directly from DFT, right? If we want to have this coexisting phase region, that's 40 nanometers. That's way out of the range of things that we can study with density functional theory. But we can kind of look at what's the transition, the phase transition, going from an S prime phase to a T prime phase. So a couple of hints that say that this is a reasonable thing to do. This is the XRD map of some of these thin films, and this is of the 002 peaks. And what you can see is that you really have this continuous set of peaks going from T prime to S prime phase. And so that shows that we probably have a bunch of structures in here that give us this phase transition between these two phases. So how do we map out this coexisting phase regions? Well, we came up with one idea of doing this. So we take the n-member compounds, we interpolate between them, and so that fixes the epitaxial strain, and then we relax the out-of-plane lattice parameters as well as to minimize the stresses as well as the atomic coordinates. And this is what it looks like for the T to R transition. First, you start off with this T prime phase. You have a bunch of structures here that actually look quite tetragonal. Then you get to this transition point, and this is exactly when the rotations along the C-axis pop in. And then once they do that, the energetics of the system just falls all the way back down to the R prime phase. One thing that we found is that if we look at where the S prime phase is, it's really not on this phase transition line. It's really out of here, and this is really to the point that it's hard to stabilize these structures within on their own. Okay, so then we looked at the T prime to S prime structure, and now we see we've got this, this clustering of tetragonal-like structures. We don't actually find a transition state here. We just get to the point where it just rotate, the polarization just, the octahedra just start, rotation just pop in, but we don't actually find something where the energy goes up. And then we see that it's more or less kind of flat as you're going between T and S, and these are all kind of S prime-like structures. And then if you can look from S to R, and it basically just falls off from S to R. And that's very similar, we think, to what you see in this XRD, right? You have all these peaks in between that relate to T prime and S prime-like structures, and then you have this fall off, and you don't really see that many peaks in this region. Okay, so now we can divide our system up into two types of regions. We can have a first region that we call our tetragonal region, or region 1, or we can have another region that's this S prime region. And so in these regions, we have a bunch of different structures that have different strain epitaxials, different strain states. This is out-of-plane strain, and different polarizations. And so we can now get an effective piezoelectric coefficient for transitions between these structures in a particular region. If we do this with T prime, we see that has no effect on the E33 coefficient. It's exactly the same as what we got with just looking at one of these structures. If we do this for R, it's very close to the pure phase. But now we see in this S prime region, we actually get an enhancement in the piezoelectric coefficient. So it really says that this large enhancement is because you have all these structures that are relatively close in energy, but they have very different polarizations. And there's actually a rotation of polarization as you go from one structure here to this direction. It's moving from sort of a 1-1-1 direction to a 0-0-1 direction. So to summarize that, here we just kind of started with something where we had some experimental information. We moved over, we did predicted properties of particularly the S prime phase. And by that, we can then look at the phase stability, the competing energies between the different phases in this landscape from the S prime phase to the T prime phase. And what we found is really you've got this flat energy landscape where you have these octahedral rotations that seem to allow for your polarization to rotate and increase. And that is what really we think gives rise to this large piezoelectric coefficient. Of course, the challenge is, can we find a material where we can basically stabilize these flat energy landscapes with these large polarizations and degrees of tilt? So just to conclude, I think the main point that I probably don't need to sort of nail home to this audience is really any approach to materials discovery, we really have to have this communication between theory and experiment. I showed that we started off just doing predictions of materials that we don't know whether they exist or not, but by having constant communication with our experimental colleagues and with also things that we found in literature, we were able to make predictions that we think are somewhat credible for making lead-free materials. And then in the other mode, we can actually start from experiment and use that to basically map out the key features of a system and provides insights into how we can sort of stabilize high response in these thin films. So future work, this is all not done. I mean, we need to start, if we're thinking about ferroelectrics, there's not really just one transition temperature, right? There are some that have multiple phase transition temperatures. And so we need to look at temperature and pressure within these materials. And so we want to start combining stochastic models with probably DFT-based models, maybe effective Hamiltonians, or even the bond valence model that Ilya talked about this morning, to examine these temperature-dependent phase transitions. So here I just want to sort of acknowledge my colleagues that helped along the way with this and funding. And maybe I'll just leave with a little bit of advertisement. So, we have two posters, one where we're looking at basically exchange and correlation effects, trying to understand, we have some insights into a new functional that might actually do very good for these, the ferroelectric properties of these materials. And also we want to look at, this is spin-driven polarization, and this is actually work that my postdoc did that came in collaboration with Joon-Hee Lee. I think Joon-Hee is going to talk about one of these materials, if he's here. I haven't seen him for the day. Later today. So with that, I will stop and take any questions.
We have time for questions. Yes, David.
Can you say again what you said about special quasi-random structures? I guess I'm curious, is that a critical ingredient, or can you do just as well by averaging over an ensemble of randomly chosen structures? And especially you're going to such multi-component systems.
Yes.
Does it get impossible to do the special quasi-random structure at some point with such complicated multi-component systems?
Right. So at some point, the short answer is that the special quasi-random structures actually didn't give us much more information than doing a 2x2x2 system. For this system, particularly because you have zinc and titanium that tend to give this ordering on the B site, we wanted to understand. We just wanted to do it just to understand what's going on. We did some work previously with potassium sodium niobate, and we did find significant help using this special quasi-random structure approach, because there we really have disordered cations. Here, it didn't seem to make that much of a difference. Is that?
Any further questions? Yes.
Do you have any idea of how these domain walls look like in BFO?
Oh.
The two lattices match at the interface.
That's a very good question. That question actually held that paper up for a little bit because we really wanted to understand what the domain walls look like. Because right now, we're kind of using static structures of snapshots along that way. What I'm hoping to do is this summer I actually have a student that's going to come in and probably do some phase field modeling of that to try to understand exactly what the domain wall effect is, right? Because as the domain walls move, then we will have some issues with how that affects the response. One thing I will say though, if you look at, so I guess Ramesh's group has a paper on where they have sort of a cartoon of what they think is going on, and they think all of the response is really in the S prime region and not in the T prime region. So basically, as you apply an electric field, S rotates into a T domain, and then when you apply the electric field in the opposite direction, it rotates back into the S phase and then into a downsized T domain. So maybe there's not so much effect of the domain wall here because we're more concerned with that S prime region. But that is something that I was curious about.
Does the boundary move when you apply an electric field, or is it sort of static?
A static boundary. That I'm not sure. So there is some change in the T prime region, but it's still T prime like, right? So you put in an electric field, maybe you get a little bit increase in the lattice in the C over A ratio, but the question is, I don't know if the domain wall moves. That's a good question.
I have a question. So I noticed that you use LDA and LDA plus U, right?
Yes.
So I'm just wondering how important is this exchange correlation functional in your calculation? So say if you get using a different functional, will you get a different results? Or?
Okay, so Yeah, so LDA was just used so that we don't overestimate things like C over A lattice constants and polarizations. Perhaps a better thing to use is PBE Sol, and then you get better lattice constants. This poster here actually shows that there's a functional called, this is like VDW-DF-CO9 that seems to do very well also for these systems. So maybe in the future we'll actually use something better than LDA, but that's what we were working with at the time, and so that's kind of why it's like that.
May I allow myself a question? Could you apply your method to PMMPT or PIN-PMMPT ternary system?
Yeah, but that one I think we're more concerned with like longer scale behavior. So you've got these polar nano regions. So perhaps that's not a good idea. Perhaps we should just kind of do what Ilya was doing and do the bond valence model.
Okay,
yeah.
Thank you. I think with that, sorry, for interest time, we have to move on. Thank you, Valentino. Our second speaker is Osvaldo Diegue from Tel Aviv University. He's going to talk about the prediction of super tetragonal phases in oxide thin film with the case of bismuth manganate.
Okay, thank you very much. First, let me thank Ron Cohen and Peter Guerin and So-Wang Yue for organizing this conference and for inviting me. My name is Osvaldo Dieguez. I have a group in the newly created Department of Material Science and Engineering of Tel Aviv University. The work I'm going to present today has been done in collaboration with Jorge Iñiguez. Jorge is a long-time collaborator of mine. We started working together when we were both in Barcelona, and now I'm in Israel. He's in the Luxembourg Institute of Science and Technology, but we keep collaborating mainly on multiferroics. So the work my group does related to ferroelectrics and multiferroics is in the first principles study of mainly thin films grown epitaxially, and mainly the role of the strain that these films have because of the substrate, and looking how dielectric, piezoelectric, ferroelectric, magnetic properties change depending on this strain. So a lot of what we did in the past and what we still do now have to do with multiferroics, and bismuth ferrite is by far the most studied one. So many of what we do is to look for materials like bismuth ferrite that can give us the same properties bismuth ferrite was supposed to have or is supposed to have, but with overcoming some of the shortcomings that it has. For this audience, I guess not much more is needed. In particular, today I'm going to talk more about part of what Valentino talked about, which are these T phases or super tetragonal phases. These T phases appear, for example, in films. This is an experimental image of a film of bismuth ferrite, where with an electric field, the film is grown on strontium titanate, if I remember correctly, and with an electric field you can move the domain walls, and you can have domain walls in between this R phase, which is very similar to the bulk phase, and the T phase. The bulk phase, again, not much is needed here, but the bulk phase has a large polarization along 1, 1, 1, and the octahedra rotate in antiphase along the same direction. The magnetic structure is the so-called G antiferromagnetic, in which the spins of the iron atoms are aligned antiparallel in any of the directions, in any of the main directions. The T phase has a structure that looks like this. It has been elongated so much that basically there's no bond between, one of the 6 bonds between iron and oxygen has been removed. So technically, maybe it's not even a perovskite, depending on how you define it. The other main difference is that the magnetic ordering is not G anymore. So it's not, all the spins are not antiferromagnetic. The ones that are in plane are ferromagnetic. The ones that are the next plane, they also are antiferromagnetic between themselves, but are ferromagnetic, in ferromagnetic alignment with the plane that is below or above. So what is it known about these supertetragonal phases? Well, they appear in several, in a few materials, or they have appeared experimentally in a few materials. In bismuth ferrite, the ones that are observed are not, as Valentino said, are not exactly tetragonal. They are usually monoclinic. So there is a there is a small distortion away from the 1, 0, 0 direction in the polarization. There is also a component of the polarization that is not perpendicular to the film, but parallel to the film. Moreover, first principles calculations show that there is not only one of these phases, but there are a bunch of them that are very close in energy. Experimentally, I'm not sure there is a conclusive result of which exact space group there is there, although, again, this is not extremely important. The space groups are, the structures are quite similar. The only changes is the degree of rotation, a small degree of rotation, or where the smallest component of the polarization points to. They all have they are called supertetragonal because the C/A ratio is always around 1.3, 1.25, 1.3. This comes with a large polarization that can be of the order of 150 microcoulomb per square centimeter, so the largest known for perovskite oxides, maybe for ferroelectrics. This polarization has been experimentally switched, so this is a ferroelectric phase, and it not only appears in films, it's, for example, the ground state of bismuth cobaltite, as is known from experiment from 2006. In this case, it's not one of these distorted monoclinic phases, it's really a tetragonal phase with P4MM symmetry. From the point of view of first principles calculations, already in 2005, the group of Nicholas Spalding, so Ederer and Spalding, predicted that bismuth ferrite should show a large C/A ratio. Again, here the phase was P4MM, which is supertetragonal. You can lower the energy a little bit if you allow the distortions, but again, there is a family of very similar phases that lie in a very narrow range of energies. People have studied then all these phases using first principles. More or less there is agreement on the results. This is from a paper by Jorge and I and 2 more researchers when we were in Barcelona, in which we studied the supertetragonal phases, or we compare the supertetragonal phases energies with other phases of bismuth ferrite. But we did this for bulk material, so not for films. We started with many different configurations of bismuth ferrite. We allowed them to relax. We did molecular dynamics to add noise to them. It turns out that bismuth ferrite has tens, if not hundreds, of phases within 300 or 400 millieV per formula unit. Among them, obviously the ground state is the R3C phase. The PNMA is very stable, and then the next most stable are according to our calculations, all these super tetragonal phases. As far as I know, this was the first time that the phases were found in bulk, and for me this explained why people were reporting films where you grew super tetragonal phases at a 7% strain. And when in perovskites, usually you cannot go over 2%, barium titanate or lead titanate. But the reason is that the phase is already metastable. So it is there in the bulk. You just have to stabilize it somehow. Looking back at the literature, this was the first instance I found of a super tetragonal phase. It's a paper by Jorge Iñiguez and David Vanderdoet and Laurent Velèche from 2003, in which they show that in bismuth scandiate and I think bismuth yttriate, there are these very large first principles results for C over A. Some of these I've redone, and I believe they are stable and they would be super tetragonal also if grown. Again, looking back at super tetragonality, there is another paper from the group of Karen Rave and David Vanderbilt in 2003, in which this also happens for lead titanate, not only bismuth, not only peroxides with bismuth, also with another lone pair ion like lead. So in 2003, they saw that if you apply a negative pressure, you basically do the same thing. That you have a lattice that at some point has to give in the vertical direction, and one bond, one way in which it gives is that one bond breaks. So they studied this with negative pressure, or another way to do it is with, as I said before, with a strain, with the biaxial strain, or with an electric field applied in the perpendicular direction, so in the direction in which the bond breaks. And the main focus on the paper was on negative pressure that at the time was not clear how it was going to be achieved. Because obviously in our computers it's as easy as positive pressure, but in experiment is not so easy. But a few months ago, there has been a paper that shows that you can do this by using the geometry of some, by growing nanowires and using a particular phase transition that exists there. You can put a negative pressure on the lead titanate, and indeed, you see the kind of results predicted. So far for super tetragonal phases, we wanted, in principle, in our search for multiferroics, so not only ferroelectrics, but also in principle ferromagnets, we wanted to look at the castings of bismuth ferrite. So in the same row of the periodic table, there is this bismuth scandiate that again was predicted to be to have a very large C over A ratio, but in bulk is a diamagnet and a paraelectric. In bulk, bismuth chromite is also paraelectric. The titanium and vanadium don't have the valence to form perovskites. Bismuth manganite is known to be in bulk the only ferromagnet in this family, but is a paraelectric. Bismuth ferrite is our friend that I described before. Bismuth cobaltite is antiferromagnet with this large C over A and large polarization. And bismuth nickelate is a very interesting metal, but it's a metal, no gap, no polarization. In this talk, I'm going to show what we found for bismuth manganite. So bismuth manganite has a very curious structure because the iron oxygen, it has very long, some of the manganese oxygen bonds are very long. So it has bonds of 2.24 Armstrongs, and then it has 4 other bonds. So 2 bonds are around that, and 4 other bonds are the typical distance in this kind of transition metal ion oxygen. So the way the reason why these bonds are so long is because the material accommodates the, well, maybe before, sorry. So this very strange pattern of bonds gives rise to a very distorted octahedra structure that you can see there. It was first believed to be slightly polar, but experiments that have been verified, and also first principles calculations, again by the group of Nicholas Spalding, show that it has a centrosymmetric group, C to C, in which the lone pair of the bismuth, which is those little rounded surfaces you see there, accommodate in a way that they neutralize the polarization. So it's in a way they align anti-ferroelectrically. Again, this gives you a polarization that is zero. As I was going to say before, the magnetic ordering comes because manganese is a D4, manganese 3 plus is a D4 electron. One of the electrons is in a EG orbital, and to avoid repulsion from the same electron in a neighbor atom, they align the lobes of the DZ2 orbital in a way that they don't point to each other, so they have this charge ordering. And this is, I mean, if you go to a good enough Karamori kind of model, you can see that this kind of arrangement will give you, I mean, again, if you allow for angles, etc., will give you ferromagnetism. And indeed, this is a strong ferromagnet with 4 Bohr magnetons per atom magnetic moment. All this, I've said, is for the bulk, for the solid. What happens when you grow this as a film? Well, when you grow it as a film, or at least some of the films show exactly the opposite behavior, in the sense that it's not ferromagnetic. You can see that it has a very small magnetism. Well, I never see the pointer anyway. It has a very small, no, it works, I think. It's just, I don't see red. But it has a very small magnetism, and at low temperature, they have hysteresis curves that go up to 20 microcoulomb per square centimeter. Again, this is not the super tetragonal kind of polarization, but it still is a very large polarization for something that is supposed not to be polar. Some ab initio calculations by, again, Nicholas group, looked at what happened when you distort the bulk structure with a epitaxial strain, but they didn't find any particular transition to another structural phase. They were interested in keeping the magnetism, so they didn't go too far away from the ground state, which is the one that is very special and keeps the magnetism. We did kind of the opposite. So we, again, ran many structures that were, some were similar to the ground state, some were very different, like in our study that I showed before for bismuth ferrite. And we compared we saw to which phases this structure relaxed, and we compared energies. We did this, again, for the typical ferromagnetic orderings that you can find in this perovskite oxide. There are 4 of them that you can see here. We use the VASP code and 40 atom unit cells. And what we found was this. So the ground state is the ground state, which is always reassuring. And is not always guaranteed, because all these calculations started with in principle, we wanted to do LDA plus U, like we always do, or GGA plus U, or PB Sol plus U. But for this material, it was impossible to open a sensible gap. So at some point, after a few combinations, we resorted to hybrids that we know that work very well for perovskite insulator oxides. And in this case, these and other problems we had with LDH plus U were solved. The price you have to pay is that these calculations are 100 times more expensive than GGA plus U. But they give, as far as we can compare with experiments, we find agreement. Things like the structure comes very well, the ground state comes as it should, etc. So what we see is, again, there is the ground state is the ground state, and then there is a group of super tetragonal phases, like in the bismuth ferrite that you can see there, that are higher in energy, and in between the ground state and these phases, there is the PNMO phase and PNMA phase, that again, as we saw this morning, appears a lot in perovskites, and the phase of bismuth ferrite with the distortions you have to have, because now you have a different ion, but a very similar phase. So here we use loosely the labels R for rhombohedral and T for tetragonal. They are similar to rhombohedral, similar for tetragonal. So all those phases are stable in the bulk again. Okay? All those phases are metastable, if you want, in the bulk. The way to stabilize them typically is to grow them as films. So what kind of films do we need? So we did a study of different lattice constants, and we found the energy for each of the phases. And again, this is very similar to what happens, or this is similar to what happens in bismuth ferrite, and we saw a graph before. There is the green triangles are the rhombohedral-like phase, like in bismuth, the ground state of bismuth ferrite. The rhombuses are the super tetragonal phase, which is higher in energy. For this particular material, that that polar ground state structure is in between the two, and obviously is the most stable when there is no strain. All the phases have a large ferromagnetic moment per ion, although they are antiferromagnetic, the ones that are not the ground state. Again, large C/A ratio for the super tetragonal phase. Band gap that is, we can see there, smaller than usual, and we'll mention this later again. Polarization, again, of the order of 100 microcoulomb per square centimeter. We also look at the pattern of displacements of the atoms that do what one would expect that they would do when you compress or you expand the lattice. So what we predict is that if you go out of the range in which the material wants to grow as a film in the same way as it wants to do in the ground state, you will have a ferroelectric with a very large polarization, both if you go to the areas of what is called tensile strain or if you go to compressive strain. There are substrates that fit, in principle, all those regions. So in principle, and again, reasoning in analogy with bismuth ferrite, bismuth manganite should be a ferroelectric when grown as a film in one of these cases. And we, or I, believe that this explains why in some experiments, although they didn't go to the region that is so low, they went to the compressive region, but not so low, they found a relatively high value of the polarization. In the paper, they describe that they detect that they have gradients of strain in their films. So it might be that at in some of the parts of the film, the strain is large enough to induce this transition. We looked at the magnetism also, the results that come from density functional theory, both in LDA or in PB salt, that are the typical things we do, give us very good results for the exchange coupling constants, when very good means that if I take the coupling constants from these little from the differences in energy between magnetic phases, and I plug them into a very simple Heisenberg model in which the energy of your material depends just on how misaligned or aligned are your spins. You get very good transition temperatures for bismuth ferrite, for example, or for bismuth cobaltite. We have tried also. And for bismuth manganite, we don't know what is the experimental temperature of transition for these kind of films, since they have not been grown. But there are no surprises here in the sense that it's a very low temperature. The Néel temperature is very low. It's of the order of the one of the ground state. But so those films that we predict they will be ferroelectric, we also predict they will be antiferromagnetic. In this case, they will be antiferromagnetic, but they will be ferromagnetic in plane. So this might have other implications for magnetism. And the last thing I want to say is that another thing that is a bit different in this material is that the band gap comes quite low for a perovskite oxide. It is below 2 eV, and I saw recently this paper by the group of Andrew Rapp in which they study the effect on the gap of rotating the polarization from a T phase, so from pointing perpendicular to a plane in a film, to an R phase. And they see that the T phase has always a smaller gap, that they relate to the presence of some 180-degree angles between oxygen, iron, and oxygen, cation, and oxygen. In our case, we see the same trend in the sense that, yes, the tetragonal phase has a smaller band gap than the rhombohedral-like phase, but in our case also, the tetragonal phase has a smaller band gap than in general any perovskite, or not any, but most of the perovskite oxides. So at some point one could think of optical applications controlled by ferroelectricity. So just to summarize, we believe that these supertetragonal phases you can find in many perovskite with bismuth, and that they are very robust and you can use them to control other properties if you want to have a ferroelectric. The particular case of bismuth manganite, we predict that they have a large polarization, and again, the particular case of bismuth manganite, the band gap is smaller than your usual perovskite band gap. Thank you very much.
Thank you, Osvaldo. We have time for questions. First, then. Stan.
This bismuth manganite strained films, it requires a huge strain, no? Or how large is the lattice constant of unstrained bismuth manganite?
So the lattice constant of unstrained bismuth manganite is 3.9.
Yeah, so
the lattice constant you need is 3.7.
So this is huge difference. And
the difference is around, I guess, like in bismuth ferrite, it must be 6% or 7%.
Yes, but classical experiments which were done, it shows a polarization. It is on polycrystalline films or practically on thick films, which claim that there is practically negligible strain. Yeah?
Well, there is no negligible. That was grown on, I think, strontium titanate.
Okay, strontium titanate, then it is 3.9.
Yeah,
so
that one is
zero
in
strain. It should
yes.
be zero strain, and it's still, in spite of it, it shows ferroelectric hysteresis loop, the films, while bulk bismuth manganite shows no polarization. So still.
So there is one of their hypotheses is that there is a gradient of strains.
But how can be here gradient of strain if the lattice constant is the same like in bulk?
Then the other possibility is I'm wrong and it was not a strontium titanate. But
okay, doesn't matter.
In any case, I mean the point I tried to make before is that the 7% difference in the strain is not that important in the sense that the phase is already in the bulk. So bismuth ferrite also has a 7% difference between tetragonal between the lattice constant of the tetragonal phase and the lattice constant of the rhomboidal phase, but you still have tetragonal films. Because the tetragonal film is not a rhomboidal film that you have managed to push 7%. The tetragonal film is another structure that is stable. It's the same way you can grow diamonds on top of diamonds and they don't go to graphite.
Can you comment possibility of expansion, of lattice expansion under oxygen vacancies? It can also induce some negative pressure.
Oxygen vacancies, again, like always in these materials, are probably there. I don't really know what the effect, whether the pressure would be large enough to change the polarization this much.
Thank you.
You say that there is essentially a broken bond in that super tetragonal, and then still is switchable. So can you comment about the coercive field, the switching mechanism for that structure, which I imagine has a very high barrier for switching?
So I don't remember the experimental values. I remember there is a paper where they show the...
You could compute you can switch computationally
yes,
and compute the barrier. I imagine that should be very, very high compared to normal materials.
All these are high. We have done it for other materials that are similar and they are high. But we know that experimentally they do it.
I was wondering if the super tetragonality is related to the Jahn-Teller effect of manganese 3+.
I never understand what exactly is Jahn-Teller. When something qualifies as Jahn-Teller or not. This, in principle, is not the typical Jahn-Teller effect in the sense that the D4 manganese ion, it has only one. Again, maybe it qualifies. It has one electron, but
it is Jahn-Teller.
It's not an octahedra anymore.
Ion.
Sorry?
It's known to be a Jahn-Teller ion.
Yeah, when it has an octahedra environment. In this case, it's not an octahedra environment. So the four bonds are identical in length. The 4 bonds in the plane, and the ion is out of plane. So if people call this a Jahn-Teller, fine.
Okay, thank you. Let's thank our speaker again. Our next speaker is Hiroki Moriwaki from Japan Fine Ceramics Center, Nagoya. He's going to talk about the first principle calculation of electrical field-induced phase transition in silver niobate.
Microphone.
Oh, sorry.
Okay. So, thank you, Chairman. My name is Hiroki Moriwaki from Nanostructure Research Laboratory, Japan Fine Ceramics Center. So, first of all, thank you for the organizer giving me an opportunity this very, very wonderful conference. And today I will talk about first principle calculation of electric field-induced ferroelectric phase transition of silver niobate. And firstly, I will explain a little bit myself wearing this not that fancy belt. To tell the truth, this is my X-ray photo. My wishbone completely broken during the skiing, actually mobile skiing training. That's so right after this conference, I need to take an operation for this portion. So this portion is very, very weak, so please be careful.
So now go back to the science. And silver niobate is known to the one of candidate material for the lead-free piezoelectric. So in 2007, and Hu and his co-worker reported this paper. So this material showed a couple of phase transition at around room temperature, and around room temperature it has an antiferroelectric phase and ferroelectric phase. Then it shows very large spontaneous polarization and very large electric field. And it shows a very large piezo response shown here. And even in a very weak electric field, it shows a ferroelectric behavior shown here. So, but many of experimental group doing research on the precise structure analysis. But those group reported in this M phase, room temperature phase, assigned PBCM. It's a not ferroelectric phase. And also another group also reported same PBCM anti-ferro electric phase in this room temperature. So we cannot explain this ferroelectric behavior of this material. And those group assigned this weak ferroelectricity because of the defect structure. But in 2011, Yashima and his group reported another solution of this ferroelectricity. They are using convergent electron beam diffraction and neutron and synchrotron radiation XRD. They assigned not this PBCM, but its ferroelectric phase assigned PMC to sub-1. So let me summarize experimental fact of this material. This material showed weak ferroelectricity at around the room temperature, and most of group assigned this room temperature phase and anti-ferroelectric PBCM phase. But some researcher, Yashima's group, assigned this ferroelectric non-central symmetric space group. So this origin of ferroelectricity of this material is not fully understood. So in this case, we are trying to understand this ferroelectricity using first principle calculation. This is our calculated result of the phonon dispersion curve, this cubic phase. This material shows very large instability, mainly rotational instability. But not only the rotational instability, but also the ferroelectric instability it has. But we can reproduce this experimental anti-ferroelectric phase, and it's a little bit very complicated structure, rotate octahedron. This according to this Glazer's notation. And it showed relatively lower energy to compare the high temperature cubic phase. So these will correspond to the experimental result. But this is an phonon calculation data for the room temperature anti-ferroelectric phase. It doesn't have any soft mode here, so we cannot explain the phonon-related ferroelectric phase transition of this room temperature phase. So, and also if we start to structural relaxation starting from this reported ferroelectric phase, but it's converged to the same structure to the anti-ferroelectric PBCM phase. So remaining possible ferroelectric origin of these materials, one of them is negative pressure, the former speaker mentioned. So this is the calculation result for the applying negative pressure. To compare the ambient pressure, it is minus 6 gigapascal. So we can find some enhancement at ferroelectric instability. But for this room temperature anti-ferroelectric phase, even though under the negative pressure, there's no clear soft mode phonon. So we cannot explain this using negative pressure. And another possibility is a defect structure. So we try to calculate the defect formation energy of this material, and it's relatively lower formation energy of this compensated silver vacancy. Silver vacancy compensated with oxygen vacancy. So if we have this defect pair, so it's generate very, very small local polarization. So under the non-zero electric field, this can be shown very, very small polarization. So this is one possibility. So we summarize those calculation results. We cannot support ferroelectric phase of this material. And this room temperature phase doesn't have any soft mode. So this phase should be a ground state structure. So the remaining possible origin of this ferroelectricity should be listed here. So defective structure, and also the one remaining possibility should be electric field induced phase transition of this material. So we try to calculate this property under finite electric field. So we are using ab init code for the under electric field calculation. Calculation condition shown here. And also we are using bus code for the NEB method. This is a calculation result for the under electric field room temperature phase. If we applying electric field this material, so this is kind of if we're applying electric field, the structure suddenly change here. So it should be electric field induced ferroelectric phase transition. And it shows very high spontaneous polarization. And if we are removing electric field, but it has also very, very high spontaneous polarization. So using this method, we can reproduce the P hysteresis loop shown here. So it's a kind of ferroelectric phase, and it shows a very high spontaneous polarization. So, but it's a calculation and it's a 0 Kelvin calculation. So structure change during this phase transition shown here. If we are applying electric field along B direction, those ions, mainly niobium, move toward B direction. Then structure change to this experimental reported ferroelectric space group. This is corresponds to the polarization switching on the ferroelectric field. This is an antiferro room temperature phase. Polarization shown here. Right, left, this sequence. But if we applying very high electric field along B direction, it shows an spontaneous polarization along this direction. This is structure change. By this structure change, but it's very, very small lattice parameter change, and relative energy relatively higher than room temperature phase. So this ferroelectric phase is not ground state. It's not that stable than room temperature phase. And this is a experimental reported structure. But this structure is not so largely displaced this niobium. This is a calculation data. So this is the ferroelectric phase, and the space will be the same, but displacement is very, very small for this experimental data. So we are also calculating the potential surface of this two phase transition. This is room temperature phase, and this is ferroelectric phase. And it has an activation barrier, energy barrier, about 40 milli-electron volt per formula unit. So if we applying electric field and then goes to this ferroelectric phase, then turn off its remaining ferroelectric phase. But this energy barrier is very, very small. So if we observe in the room temperature, maybe some portion of this ferroelectric phase goes back to the anti-ferroelectric phase. So this is a calculated PE hysteresis loop, but it's quite different from experimental observed hysteresis loop. Maybe in room temperature, this ferroelectric phase goes back to this anti-ferroelectric phase. So we are assuming this material at room temperature, this anti-ferroelectric phase and the coexistence of anti-ferroelectric phase and the ferroelectric phase. So now we can understood this P hysteresis loop, this type of mixture, coexistence of anti-ferroelectric phase and the ferroelectric phase. So this is a experimentally reported structure. This portion, a lower portion of difference from our calculation result. But if we considering this two-phase mixture, so maybe experimentally observe kind of this average structure maybe. Let me summarize our calculation data. The possibility of electric field in this ferroelectric phase transition, this material studied using first principle calculation. So electric field in this ferroelectric phase transition may be occur in this material. And the polarization and the EV is very, very large, and it's well corresponds to the experimental data. And the ferroelectricity of this material can be explained by coexistence of ferroelectric phase and the antiferroelectric phase. And also, now we are doing first principle molecular dynamics simulation using VASP code and calculation detail over shown here. But it's an ongoing calculation. So it's very, very preliminary data also. But we showed a little bit about this one. And finite temperature, this is the bond length change. This is a niobium, and depending on the temperature, this structure change. So polarization switching, and this one, and this one, and this one. So. And this is an polarization switching frequency in our first principle molecular dynamics simulation. So if temperature goes up, polarization switching frequency goes up. And at around the room temperature, polarization switching were found. And this is averaged polarization of this system. So if we starting initial structure, this on the ferroelectric phase, temperature goes up and average polarization goes down. So this is a clear evidence for the coexistence of this two phase. Now, this is some acknowledgement, and we will have a conference next May. This is AMTC5, the 5th International Symposium on Advanced Microscopy and Theoretical Calculation. So one of our Dr. Ronald Cohen will come to make an invited talk in this conference. This conference and focus on the microscopy and the theoretical calculation. If we are interested in this conference, please come and join us. Thank you for your kind attention.
Thank you. We have time for one question. Fanny. Yes.
I have a very simple question. How technically you introduced electric field in ab initio calculations?
I'm not a specialist for the theory, but maybe
because as far as I know, it's not incorporated in both codes you mentioned.
You know exactly. I cannot explain. Okay. That is very, very difficult for me.
Maybe you can discuss at the topic break. For interest time, let's move on. Please thank our speaker again. So our next speaker is Yong Pa. And he's going to talk about, on behalf of the Jung Hee Lee, who unfortunately could not come. And he's from Ulsan.
No. Okay, so let me explain. So I got asked to do a talk instead of him, but this is nothing related to his original work. I just asked can I contribute to the talk for this missing
Okay,
session.
so a different talk from the original program. And he will
right after this lunchtime. So please, spare me if I'm a little bit disorganized. So. Okay. Where is it?
ありがとうございます。Sorry.
My name is Hae-young Park from Rutgers University, and then I would like to talk about charge order-induced ferroelectricity in lanthanum vanadate and strontium vanadate superlattices. So let me start with a brief introduction of charge order-induced ferroelectricity in, for example, bulk oxide. The simplest example would be the linear chain of atoms, and let's think of first neutral chain of atoms where there's no polarization, definitely. And we can think of, let's say there is some induced charge-centered, size-centered charge order. Then we can see there's charge order, but there is inversion center, so we don't expect any kind of polarization. And also we can think of a bond-centered charge order or kind of the dimerization where there's no net polarization also. But if we combine these two polarizations together, and in this structure, there is no inversion center, so this allows polarization in this direction. So the category of a compound I am interested in is polarization induced by charge order, where more narrowly, polarization is mostly induced by the charge transfer itself. For example, this is schematic picture of magnetite, and this is paraelectric phase, and right-hand side the ferroelectric phase. And if you see that, as you can see by comparing these two, do you have the other one? And then you can see there is a charge transfer from here to there, and also over here, the same thing happened. And so it will give about 5.7 microcoulomb per centimeter square about order of polarization. And the other example is the organic charge transfer sort. If you look at the lower figure, and then this is composed of two type of molecules, which is TTA and CA, and then the ferroelectric transition incorporate the charge transfer between this ion and the other ion. So this will induce the polarization about 5 microcoulomb per centimeter square. So the question is, because I'm trying to relate this idea to the oxide heterostructure, and especially superlattices, and I want to argue why oxide heterostructure or superlattice is the ideal platform for this type of charge order. First, in many cubic perovskite bulk transition metal oxide, this kind of charge order ferroelectric polarization is prohibited by high point group symmetry of the crystal. But forming the superlattice has the advantage in twofold advantage. One is it enables to control the fractional balance of transition metal d orbital, meaning that I can control how many electrons in the d orbital. And secondly, because of this superlattice layering between let's say two compounds, we can introduce additional symmetry breaking, which is important for the charge order induced ferroelectric polarization. On top of this fractional balance controlled by superlattice layering and the strong Coulomb interaction, the system will prefer the integer occupancy, nominal integer occupancy of d orbital, and which may emerge the ferroelectric polarization by breaking additional symmetry. So the compound I am trying to discuss now is 1,1 superlattice of strontium vanadate and lanthanum vanadate. And briefly, lanthanum vanadate is multi-insulator with 2 electrons in the vanadium d orbitals. Band gap is 1.8 electron, but this is calculated value. And strontium vanadate has 1 electron in vanadium, which is correlated metal with cubic symmetry. So if we have 1,1 superlattice with lanthanum vanadate and strontium vanadate, average occupancy of vanadium is 1.5 electrons. That means with a strong on-site Coulomb interaction, charge ordered insulating ground state with half of vanadium with 3+, half of vanadium with 4+, would be favored. So there is a schematic of what kind of charge order and orbital order pattern would emerge, which is consistent with vanadium 4+ and vanadium 3+ charge order. For example, this is atomic structure of 1,1 superlattice of lanthanum vanadate and strontium vanadate. I have 1 layer of strontium oxide layer and 1 layer of lanthanum oxide layer, and then in between there is vanadium VO2 layers in between. So if we assume that half of octahedron are elongated in z direction and half of them are contracted in g direction, this is what we expect of the orbital order, which break the symmetry of degenerate T2G orbital to xy and xyz. Because all the site is presumably spin polarized, but this elongated site will have a 2 electron which occupy x and yz orbitals, and for this site, it will occupy xy. It will occupy xy orbitals. So this kind of distortion is consistent of V4+ and V3+ charge order, and I will show this is what is actually happening. So, and then the question is, what kind of charge order pattern it will have if this kind of distortion and orbital charge ordering exists? So, the most obvious charge ordering pattern is three-dimensional Chekhov order, where A site, as I briefly mentioned before, is layered cation ordering, alternating lanthanum strontium and lanthanum strontium ions. But vanadium atom has charge order where I have all the nearest neighbor of vanadium 4+, vanadium 3+, and vice versa. But in this configuration, there is the polarization in the Z direction is not allowed because I can have inversion center somewhere over here. And then this is the most obvious case, but let me explore another possibility, which is layered charge order. So this is the layered charge order configuration where A site is same, I have layered cation ordering, but B site, I have alternating sheet of vanadium 4+ and vanadium 3+ and vanadium 4+. And if you look at this structure, all the inversion center, which was present in the Chekhov type of charge order, is missing in this kind of structure. So that means this structure allows polarization along the Z direction. So in the other way to say this is, first, layered cation ordering of a superlattice lower the symmetry first. Then on top of that, if layered charge ordering breaks the additional symmetry, then we can have a structure which allows a polarization in the Z direction. So, and the question is, okay, we can have two structures, but maybe this structure is much low in energy, so this is much higher in energy. That's maybe the next question. What is energy difference between these two structures? And here, this is energy for each. This is energy for basically this is energy for vanadium for the Chekhov the charge ordering and the layered charge ordering with the various type of magnetic order. So I will not discuss why these energies are very close to each other. Basically, this is argument of Goodenough-Kanamori rule, and you can see where you can kind of make sense why these energies are kind of close together. But over here, the main message is the energy difference for vanadium or energy difference for formula unit cell is like a formula unit cell is twice the number of vanadium. So this is about the 5 milli-electron volts per formula unit cell. So these two structure has very small energy, even though it has completely different charge ordering patterns. And then also we calculate the polarization of this phase using Berry phase method, and then the calculated polarization is comparable to the barium titanate, which is around 34 microcoulomb per centimeter square. So there is sizable polarization, and also this value is consistent to the charge actually. Over here, the difference between these structures is basically there is charge moving from here to there. And then we can get this structure, and then if you compare this polarization with the nominal change in the vanadium occupancy plus this distance, and this is the close value of this kind of electronic-driven polarization. So the other thing which supports the consistency with this small energy difference is density of state. Basically, I'm showing the Chekhov and layered in the CAFM state, which are one of these dots, and then this is CFM of layered charge order, and then the basically density of state is on top of each other. That means that it's consistent with the small energy difference between these two phases. And but we want to know how similar these two phases are. So here I am basically comparing these two octahedron with the two different phases, and then so basically what I'm showing over here is the distance between vanadium and the neighboring oxygen in all 6 directions. And so these, and then all the smaller octahedron and the larger octahedron, but and then I will put for the CCO phase is our solid line and LCO phase are the dotted line. And the message over here is these are on top of each other. That means the octahedral the distance between this atom and this atom, this and this atom is basically same over here, and these are same as over here, and these are same as over here by proper permutation of the symmetry. So that means structurally, this and this is just the difference between these two phases is kind of rearranging all the octahedron in a different manner. So that's why it almost has the same electronic structure, but only the pattern differs each other. So here is another supporting argument of how the okay, so over here, and then the G direction, I have two sets of G's larger, which is correspond to this, and then the two sets of G's smaller, that's this for this octahedron. That means basically this kind of charge ordering is assisted by or induced by this elongation and contraction in the apical oxygen in the G direction. This apical oxygen in the G direction give you clear, very clear orbital order. For example, this is vanadium 4+ site, and because this is compressed in the G direction, the XY orbital is occupied while XG and YG orbital is above the Fermi level. And whereas vanadium 3+ site, the XG-YG orbitals are occupied where XY is empty. So, and then because each site are completely polarized, the magnetic moment is proxy of what's the strength of charge order. So vanadium 4+, the calculated magnetization is 1 Bohr magnet, and vanadium 3+ is 1.8 Bohr magnet, meaning that it's almost 1-2 vanadium D1, D2 charge order. So another question can be arised from this calculation is how they switch to each other. So this is energy for vanadium, and then I'm showing this along with the parameter lambda, which is basically structural interpolation from the CCO phase and LCO phase. So this will give first the energy barrier for vanadium is about 50 millielectron volt, and second, this is the gap while we interpolate this structure from CCO and LCO. And interestingly, the gap is there is finite gap along this transition, so there is some insulating path, at least simply insulating path exists. And the nature of the transition is following, because what happens is basically these two vanadium 3+ and 4+ kind of change the balance by the moving oxygen from like up and down, and then make this down, and then so then this vanadium 3+ 4+ exchange with each other. That means the magnetic moment of these two vanadium will switch around 0.5, lambda is 0.5, and then it suddenly the transition happens suddenly. That means first order phase transition, and which is also consistent with this lambda type of transition. So the other degree of freedom, because this is can be epitextually grown with some substrate. So natural question is what is the strain dependence of these phases? And this is energy versus epitextual strain with respect to bulk lanthanum vanadium lattice constant, which means 0 over here. Then, as you can see in the negative strain, like CCO phase is lower energy, but if we put the tensile strain, at least we can make these two energy degenerate. That means we have some epitextual strain control the charge ordering and ferroelectric polarization, and also it enables to stabilize LCO phase by applied electric field. So here's summary. So I start with this kind of argument by combining two types of charge order, we can have a structure which allows the ferroelectric polarization. And we kind of show that this is possible by having two types of symmetry breaking. One is superlattice layering, then charge ordering on top of that. So if we combine these two structures, we can have the structure with ferroelectric polarization, whose value is 34 microcoulomb per centimeter square. And then we have also how this is, we study how this is related to structure distortion and then but I want to just stress that what we found is antiferroelectric state, not the ferroelectric state, because after all, like a Chekhov charge order state is low in energy, but we can make this phase as close as possible, so which allow us to switch these two polarization states. Thank you.
Thank you, John. Good questions? Yes.
One of your first slides, you mentioned these materials are highly correlated. You also said Mott insulator. So I wonder why, so one of the very first you have shown
Right.
this one.
Yes.
So, and then instead you approach them by standard density functional methods, it seems to me. So why?
Right. Okay. So that's a good question. So multi-insulator state. What I mean by multi-insulating state is low temperature ground state is reasonably well described by DFT plus U calculation. So I use DFT plus U calculation with Coulomb U is 4 electron volt. So in that case, I mean, I'm not saying this compound is multi-insulator, meaning that in the high temperature, it can be insulating without any static magnetic order. For example, lanthanum vanadate. But that cannot be captured by DFT, but at least low temperature phase, in which there is a static magnetic ordering, can be described in DFT plus U calculation.
Any further questions? Yes.
Just a follow-up on that. I mean, I'm convinced for the case of the D2 vanidates, but for the D1 vanidates, are you sure that a value of U of 4 eV is appropriate? I mean, especially in the superlattices, you've got this charge ordering, you've got 2 different vanadium sites, and is it possible that, you know, each vanadium site, the 3 plus and the 4 plus might require different values of U? And did you check with perhaps
I mean,
hybrid functional or?
Okay, so I'm not sure I understand the question correctly, but if the question is how sensitive this result with respect to U, is I can say this is insensitive with respect to the change in U value.
But how about affecting, changing the actual U on the 2 different sites? So, for example, if the D1 site required a U of 5 EV, but the D2 site required a value of U equals 3 EV, would that change?
Okay, so the definition of the Coulomb U is, so your question is whether Coulomb U is changing with respect to occupancy of the orbital itself. And as far as I know, it's not changing. Because there are other competing things. So there is J, and then there is J over there, and then there is Hund coupling, and then this kind of interaction is also considered in the Hartree-Fock type of the DFT plus U calculation. This kind of on-site correlation is already in there.
Okay, I think that's a continued discussion at the coffee break. Please join me in thanking all speakers of this session. We take a short break. Yeah, Peter will give us some announcement.
I just want to make sure that I've gotten all the people who want to register for the poster competition. And I recognize that not everybody may be here, but I'm just going to go.
Oh.
Yeah. So we have so far 16 people. I'll just go by last name, and if I don't call your name, let's just come see me. So we have Ablett, Dreyer, Glaskova, Hendricks, Herchig, Kalfarizi, Casey, Krogstad, Patel, Prokorenko, Chi, Syed Agi, Skiadopoulou, Sirikas, Tillich, and Walter. So did I miss anybody? Okay, good. Good luck.
Okay, just short coffee break. We come back at 5:20, please. Yeah, that's fine. I hope. It's too weak, I think, because the screen is very bright, and then it works, but it's.
So what did you just?
I borrowed Peter's, so this is a little better. So
Okay.
Just make sure that they don't take it and bring it back to Peter. Otherwise, the photo mic is working.
Go to. 那个 poster competition。我一看，你先去。对啊，你现在可以去啊，现在还在。
competition.
No, I don't think because it really was hard. The previous part then. I didn't have, but there's a step, but step.
This thing, people are complaining that it's not really bright enough to show on the screen, so we're borrowing. I think this is Peter Garrett. Oops. Wrong way. Is it off? Oh, here it is. You press the you press the sun. Okay. So people have been using this as a pointer, and I might as well get you wired up with this. Try not to say anything rude in the next. Is it possible to reverse this? Can't they reverse? No. Because here, I'll just do it this way. I guess it doesn't matter. How do I do that?
Well, I think we should get the session underway. We have 3 more talks late this afternoon on high throughput calculational techniques. The first talk is by Kevin Garrity at NIST, High Throughput First Principle Search for New Ferroelectrics.
Thank you. Good afternoon, everyone. My name's Kevin Garrity, and I'm going to tell you about some work I've been doing at NIST on using high throughput techniques to search for new ferroelectrics. So this talk is going to be a little different than most of the talks so far. I'm going to talk briefly about a large number of materials that are not perovskites. So get ready for that. So in the introduction, I'll just give you some background to the first principles techniques I'm using, how I'm using high throughput computation to identify ferroelectrics. Then I'm going to move on to the two search strategies I'm using to identify ferroelectrics. And along the way, I'm going to give you some examples of interesting materials I've found. So, of course, you all know that ferroelectrics are materials which might have some sort of high temperature nonpolar structure. A low temperature, the ground state will be polar. And then, crucially, you can switch the polarization with an external electric field. So if we want to identify ferroelectrics from first principles, and the first thing we need is it needs to be insulating so we can apply an electric field. Again, we need to find a material with a polar ground state, and then we also want some sort of higher symmetry structure which is close in energy to the ground state. So we're going to use that as our criteria that the material is likely to be switchable. So this doesn't exactly describe how materials switch in experiment, which might involve things like domain wall motion or domain nucleation. But this is still a pretty good indication that a material is likely to be ferroelectric. So some well-known examples, perovskite ferroelectrics have energy differences. So the units I'm going to use are MeV per atom, and they're in the range of 4 to 20. We heard earlier about this calcium titanate, Ruddleston Popper, has a slightly higher energy difference, and also some of these binary oxides. So different types of ferroelectrics all tend to have this small energy difference between the high symmetry and low symmetry structures. I'm not going to spend a lot of time motivating why we might want to find new ferroelectrics, but they could be useful. They could indicate new ways to make multiferroics, piezoelectrics, or they could include new phenomena entirely. So the database I'm going to search for new ferroelectrics is the ICSD, the Inorganic Crystal Structure Database. So this has a lot of experimentally determined crystal structures. So all of the materials in this talk have been synthesized in at least one of their phases. So they're not things I'm just pulling out of thin air. So this database is maintained down the hall from me at NIST. And so, known ferroelectrics will mostly have both polar and nonpolar phases listed in the database. New ferroelectrics, they're candidate new ferroelectrics, will of course typically only have one phase or the other listed. Otherwise, someone probably would have identified it could be ferroelectric. And we need some sort of computationally efficient way to search through this database, or at least limit our search to interesting regions of phase space. So a few computational details. This work is done with density functional theory. I use the PBE-SOL exchange correlation functional. I use the GBRV high throughput pseudopotential library. So this is a pseudopotential library that I put a lot of work into when I was at Rutgers. It's available at this website if you're interested in it. And I do linear response phonon calculations. So the first search strategy I'm going to use is I'm going to start with a known polar phase and look for, I'm going to start with a known nonpolar phase and search for potentially overlooked polar distortions. So the idea is we take nonpolar materials and we first do a gamma point phonon calculation and look for unstable polar modes. So we start with some sort of high symmetry structure, look for an unstable polar mode. If we find an unstable polar mode, then we can go on and do a full phonon calculation and look for any additional instabilities that could compete with our polar instability. And then once we have this, we can, in a somewhat well-known but tedious procedure, try to find the ground state by relaxing in different combinations of phonon modes. Or if the phonon dispersion becomes very confusing, you can augment this with random searching to make sure you're not missing anything. But the basic idea is we want to find a material with a previously unrecognized polar instability, which leads to the ground state. Or if there's a competing antipolar phase, we could have an antiferroelectric. So we can't just apply this to every material in the ICSD. So the reason I started this work is I already had a bunch of phonon calculations from this earlier study I did on oxide thermoelectrics. And I noticed that some of these already had unstable polar modes. So I took these materials, which consist of these transition metals plus oxides, sulfides, and nitrides of those transition metals, supplemented them with a bunch of similar materials which have small unit cells, so the calculations take a small enough amount of time. So here are some of the positive results from this search strategy. So in this case, the high symmetry phase is observed in the database, and then this is the chemical formula. This is what I find is the ground state. This is the energy difference in MeV per atom. So you can see they're all in the range where they should be, and they're potentially switchable experimentally. This is the polarization in microcoulombs per centimeter squared, and then a little bit of information on the energy of any competing antipolar phases I found. One of these materials, when I did a more thorough literature search, I found that it had previously been studied and shown to have a ferroelectric hysteresis loop, but its polar phase had never been determined accurately. So that's why it didn't show up in the database. So you could count this material as a kind of retrodiction. So I'm going to go through a few examples of these materials. So this strontium niobium oxygen compound, it has this fairly complicated unit cell. So if you look carefully in plane, it has a fixed polarization, but that's not the switchable part. So the switchable part of the polarization is this out of plane. So you have these niobium oxide layers, strontium oxide layers, and you get a bunch of different unstable modes rumpling in this niobium oxide layer. So this material has a couple of interesting characteristics. So the first is that it has extremely high Born effective charges. So this is, of course, typical for perovskite ferroelectrics, if you're familiar with Born effective charges in those materials, but this is less common in other families of ferroelectrics. And you get some of these extreme, like the niobium Born effective charges, depending on which one you're looking at, can be all the way up to 11, according to the calculations. Second thing is that this material has some interesting dielectric behavior. So it has unusual LO-TO splitting. So the TO modes, or under E = 0 boundary conditions, there are 4 unstable modes at the gamma point. One of them is antipolar, and then the other 3 are polar. So I'm listing the frequency and the mode effective charge. So you can see these materials have very large mode effective charges. But what was surprising is that when we move to D = 0 boundary conditions, or LO modes, we still have 4 unstable modes. It's just the polar modes have all mixed with each other in order to reduce their Born effective charges. And so this material is similar to a class of materials called hyperferroelectrics, which I've written a paper on in the past, and it has similar behaviors, but it looks different in practice. So it's an interesting material. One more example, this yttrium sulfur fluorine compound. It's a hexagonal material. It forms these layers, and the energy lower in distortion is a locally antipolar buckling in these yttrium fluorine layers. But because of the way the layering in this material works, these two atoms are not crystallographically the same. They see different layers above them. So this turns into a weakly polar distortion. So depending on the way the different polar distortions line up, you can either get a polar phase with a pretty small polarization, and this is nearly degenerate in energy with the same thing but with antipolar distortions. So I don't know if this is useful for anything, but it's pretty interesting. So the second search strategy I'm going to use is start with a known polar material and then look for previously unrecognized high symmetry phases, which could indicate that the material could be switchable. So the way I'm going to do this is I'm going to just take a bunch of known polar materials and do a symmetry analysis of them, looking for symmetries, and basically adjust the tolerance factor upwards to look for more and more hidden symmetries. So start with a polar compound, look for hidden symmetries, and then if I find good candidate structures, I can calculate the energy difference, and if the energy differences are small, the material might be switchable. So here are some positive results from this search strategy. Again, in this case, the polar space group is observed experimentally, and I've identified potential high symmetry space group, and then you can see again there are a lot of small energy differences, and the polarizations range from extremely small to quite large. So the first example I'm going to show you is this lead aluminum oxide compound. So the top view, it has a hexagonal symmetry. This is the nonpolar side view, and then in the polar phase, what happens is the polarization comes in plane because the AL the aluminum-oxygen tetrahedra want to adjust their bond lengths in plane, so they all tilt, and they tilt in this cooperative manner, which causes a polarization. So an interesting thing about this material is that it has 3 in-plane polarization directions it can sit, and there are also 3 metastable polarization directions rotated 60 degrees. And then, so this metastable direction is only 8 MeV per atom higher. So you can rotate the polarization in this material. Instead of switching it through the high symmetry structure, you can rotate the polarization. So that works kind of like this. It's a little hard to see the atoms, but this is showing the polarization starting this way and rotating around like that. So switching, the switching barrier using this technique or using this switching path is an order of magnitude lower than going through the high symmetry structure. Second example, this is another material that ended up, when I did a full literature larger literature search, ended up having been previously studied as a ferroelectric material. So this is the antimony tungsten oxide, and so this material was in the database, but under just a P1 symmetry, and I found these 2 higher symmetry versions. So this is a polar phase. You can see that this oxygen-tungsten-oxygen bond is not 180 degrees, where I've identified a higher symmetry structure where this bond is 180 degrees, so the structure becomes nonpolar. Here's another example. So this is 3 views of a potential high symmetry structure, which I've identified from this vanadium molybdenum oxygen compound. So this material has a polar phase listed in the database, and it has this extremely large polarization. So you can see basically all of the oxygen have moved to sort of change the coordination. This sort of looks like these super tetragonal perovskites in a way. There's another phase listed in the database. So this is an antipolar phase. So this one is the ground state, and then this is listed as a high temperature phase. And so it would be interesting if you could switch between these 2 phases with an electric field. You could get a very large response that way, potentially. I also discovered a 3rd phase. You could consider this a kind of ferroelectric phase, where the molybdenum oxygen chains are polarized, but the vanadium oxygen tetrahedra are antipolar. And one last example, this is a lithium vanadium oxygen compound. And so in the high symmetry phase, it looks like this. The major change is the lithium off-centers in this direction, leading to actually relatively large polarization when you consider how small the energy difference is between these 2 phases. And so one interesting thing about this compound is, at least in my initial calculations, it appears to be a ferromagnet. So this would make this material a potential multiferroic, although I have to do significantly more work to actually establish that. So in conclusion, I've told you about my high throughput search for new ferroelectrics. I've gone over the 2 search strategies I use, and then I've given you a bunch of examples with interesting physical phenomena. Thank you for your attention.
Are most of the new ferroelectrics you found, do they crystallize in hexagonal symmetry, or there is no general rule? I
mean, some of them have hexagonal symmetry, but not in general, no.
So you can find in any crystallographic system, according to you?
I mean, I've found structures with the only symmetry in the high symmetry phase is inversion. So all the way down to the lowest possible symmetry.
Thank you.
Could you tell a little bit about how do you calculate phonons, technically? I mean, is it WASP, GJ plus
So I did the calculations with quantum espresso and their linear response calculations.
Okay. But did you try different functionals or which functionals?
I only have used PB Sol in this work.
Did you compare with other functionals like
I haven't compared with other functionals. So far, I've been concentrating on identifying interesting compounds. And if people tell me they're interested in making the compounds, I'd be happy to do more calculations to make sure that they are, make sure the results are robust to different functionals.
Other questions? Good. Sitting all day.
So this was, you were using the international database as a source?
The ICSD?
Right? Yeah. So I was always wondering, if you look at the back of Lines in Glass, there's all these ferroelectrics, some of them with question marks. Have you ever gone through that list?
I mean, I've looked at it before.
Anyway,
I haven't gone through it systematically in this way.
I assume all of those are in the database, but anyway, it would be nice to just have an updated list and remove some of the question marks, with the yes or no or something.
One quick question. You mentioned the ferromagnetic compound at the end. Some of the other ones, were they also magnetic or antiferromagnetic?
These ones were, all the other ones were non-magnetic.
One final question, or should we move on? Okay, thanks then. Thanks, Kevin. John, I think. So the next talk will be by John Bonini, Efficient Computation of Spontaneous Polarization Using 180 Center Displacements.
Let me go grab, oh no, here we go. Oh, I need to go grab an adapter. Okay. Should have taken that off. Is this Kevin's? I don't know. Okay, can I give you the mic? Yeah. And people have been using this. It's the little sun as the pointer. All right, great. What's going on here? So let me go to split. Let's mirror these together. Okay. All right. Cool.
Hello. I'm John Bonini. I'm a graduate student of Karen Rabe at Rutgers University. I work in the group of both Karen and David here on first principles material design. So I want to thank the organizers of this event for giving me the opportunity to tell you about a project that had its origins with, I'm moving ahead here, that had its origins with a former postdoc in our group, Oscar Paz. So this is a method where we use the displacements of Wannier centers to more efficiently compute the spontaneous polarization of ferroelectrics. So what is the spontaneous polarization? Now, I guess if there were ever a room full of people that all knew the answer to that question, this would be it. But I'll go ahead and say it anyway. The spontaneous polarization is half the change in polarization as a ferroelectric switches between its oppositely polarized states. So here I have everyone's favorite perovskite here. I can't get rid of this. Okay, cool. Oh, great. So I have everyone's favorite perovskite here, and that's going to try to switch forward. Okay, that'll go away. Hopefully this will go away. Great. So I have everyone's favorite perovskite here, and I show the up and the down state. And indeed, this spontaneous polarization, which is the change in polarization between these two states, is the value that can be measured by an experiment. So experimentalists would go ahead and apply a voltage across the material. This would move the charge to change it between these two states, and this movement of charge is itself a current, which is then measured. So this is the first principles section, so we don't want to just measure this experimentally. We'd also like to be able to compute it from first principles. So thanks to Rafael Resta and David Vanderbilt here, we have the modern theory of polarization, which starts by, we can think of starting as by defining this value for formal polarization. Here it's written in terms of block wave functions, and this integral is closely related to a Berry phase. So we can write an equivalent expression for this, we can write an equivalent form of this equation in terms of Wannier functions. So where here this R is called the Wannier center, which is the position expectation value of the Wannier function. So just like the ionic positions here, the Wannier center is only defined modulo a lattice vector, where in a crystal we have periodic boundary conditions. So as a result, this formal polarization is only defined modulo what we call a polarization quantum. So this polarization quantum is equivalent to taking one unit of charge and moving it by a lattice vector. This is, you're moving some charge, so you're changing the polarization, but if you move it by exactly a lattice vector, you bring the bulk system back onto itself, so it's still the same system. So this formal polarization sort of has to be a lattice-valued quantity. It's not a vector, it's a lattice. So we want to find the spontaneous polarization, though, not just this formal polarization, because the spontaneous polarization is what can actually be measured in an experiment. So here I've drawn the, the spontaneous polarization is half this change in formal polarization. But, okay, so I write this, I have a plot of this formal polarization, if you can think of as some one-dimensional material, or maybe just the polarization along one particular direction of a 3D crystal. And so I have the polarization lattice, the formal polarization lattice. I said it's only defined modulo this quantum, so we need to have a full lattice of values that characterize this one state, and here's the polarization lattice for the up state. So I want to take the difference between these two lattices, but this is sort of problematic. If they were single-valued quantities, then I could just subtract them. But here, it's a multi-valued quantity. How do you take this difference? I mean, presumably it would be you take the value of one of these up states and subtract it from one of these down states. But you can see the problem already. There are several ways to do this, and you'll get a different answer each time. So these each correspond to a sort of a different branch choice of the lattice. So we need to know how these two lattices are really connected. And experimentally, this is related to how the material actually switches between these states, like what is the actual process by which it moves between the up and the down state. So it might be natural then, and this is the way most people currently compute the spontaneous polarization, is to pick some path that the ions take and compute this formal polarization along that path until we eliminate this ambiguity. So you might pick a high symmetry reference structure that the material moves through, and now here I did that and I eliminated one of these possibilities. But you can see there's still ambiguity here, so we can compute more intermediate values, and eventually we can settle on a particular branch choice of how these lattices are connected. So this is quite computationally expensive, and we're talking about some path to connect these that usually doesn't really correspond to the actual physical path the material takes. Real materials switch through usually domain wall motion or something like that. But nevertheless, this procedure usually does get values of the spontaneous polarization that agree well with experiment. So you might even ask, why does that work? And you might ask further, why are we computing information about all these intermediate steps that don't even describe the physical path? So what we can observe is that this procedure would describe a type of switching which has overall minimal movement of charge in switching between the up and the down state. And that is indeed what motivates the method that I am going to talk about today. So I told you before that we can describe this polarization in terms of Wannier centers. So the idea is that we can perform the calculation for a single structure, obtain all the Wannier centers, and then some reasonable movement of these centers between the up and the down state will indicate what branch choice we should take. So here I have a sort of toy crystal system with an up and a down state here. And there are two ways that this red Wannier center can move to switch between from this up state to this down state. They could both move up, or not both, but everything in the whole periodic lattice, or they could move down. So the sort of reasonable movement here is going to be this minimal movement of charge overall. So we want to choose the path which minimizes the sum of the absolute value of the difference between the centers in the up and the down state. And maybe this is obvious, but the contribution of each center to the spontaneous polarization will be its charge over the cell volume times its displacement. So just like atoms, Wannier centers can be described in terms of Wyckoff positions because we have some symmetry of our crystal. So in the previous example, the red dot was a Wyckoff center with multiplicity 1. If we have higher multiplicity Wyckoff centers, we have to consider how the whole set in the up state maps to the whole set in the down state. We can't just handle them one at a time. So as before, we could have everything sort of move together all down, or everything move all up, or we could have, if we can further minimize the overall displacement by letting them sort of swap their flipped images to still transition from this up state to this down state, and then I'm saying that's the path that we should choose. So the method sort of in a more algorithmic sense is, one, we only have to use one DFT calculation. We're not computing all these intermediate steps. And we start by grouping all the centers from what we'll call the up structure into symmetry equivalent sets. And then for each set of equivalent centers, we will mirror them, or whatever operation maps the up structure to the down structure, and find the one-to-one mapping, so allowing them to kind of exchange their mirrored partners is what generates all the different mappings. But we want to choose the mapping which will minimize this sum. Furthermore, because the other method would, at least when you just do it in terms of interpolating ionic positions, it'll preserve the symmetry of the crystals throughout the whole switching process. If we want to have agreement between the two methods, we will also constrain this minimization that the symmetry of the crystal is preserved entirely along the switching path. Finally, we would sum the differences in position between all pairs and all groups, multiply by their respective charge over the cell volume, and obtain our spontaneous polarization. So I did these calculations using density functional theory, starting with density functional theory using quantum espresso and Kevin's GBRV ultrasoft pseudopotentials, so thank you, Kevin. And then used Wannier 90 to obtain my Wannier centers. But this method could in general work with any code that interfaces with Wannier 90. So here are a few and not even all codes that interface with Wannier 90. So how well does this method work? So here's an example for a small handful of materials, starting with some more well-known perovskites. But then also we want to expand to other types of structures so that we can do this for these interesting structures that Kevin just showed us as well. Here are this is a hexagonal structure, and this is boron nitride, which isn't really a ferroelectric because it doesn't switch, but it was sort of a good exercise. At least I first considered it just an academic exercise to say, if you could switch boron nitride, what would its polarization be? But there's actually a poster here today from Cyrus Dreyer where he needed to compute the spontaneous polarization of or at least compute a value of the polarization for Wurtzite type crystals to use. So all these values on the left here had to use, maybe 5 times, 10 times as many intermediate steps, whereas this calculation just uses one and then analyzes the movement of the Wannier centers. So this is kind of a weird picture, especially if you're expecting all of these to be atoms. In fact, only the blue and green circles are actually atoms. So this is the boron nitride picture, where these black and purple dots are the Wannier centers that are colored by their symmetry, and then these arrows show the sort of smallest movement of charge switching path to go between up and down. So you might have noticed that for boron nitride in particular here, these numerical values aren't in perfect agreement, so perhaps this method doesn't converge quite as quickly with maybe k-point sampling as does the more typical method, but these differences themselves fall onto a lattice that's determined by the polarization quantum. So if you're really worried about this numerical difference, maybe you can use this method to make your branch choice and then use the numerical values from just the usual Berry phase calculation. So for this method to correspond well with experiment, we need to meet two conditions. The first is sort of the one that was kind of the main point, which is that the physical path corresponds to a minimal net displacement of charge, and furthermore, this movement happens without breaking symmetry. We also need there needs to be the physical path must be insulating throughout the switching process. In this case, we're not computing things along the path, so we just assume some insulating path exists, and it corresponds to this minimal net displacement of charge. So for known typical ferroelectrics, these assumptions are empirically justified. So this isn't, in general, this isn't a theorem that all ferroelectrics have to switch in this way. It's just that we're capturing the same physics of this sort of standard way of constructing a one-dimensional path between the up and the down state with much less computation. So really, there's nothing in the theory that prevents more exotic switching processes from happening. I just don't know of any materials that do that. So maybe you have some path that breaks this symmetry assumption, and you might have some interesting, there might be some interesting property that results in switching between up and down along one axis and then having an in-plane current perpendicular to the way the axes where the polarization was switched. Or if you want to relax this minimal net displacement of charge, that means in going from the up and the down site, charge moves not just by the minimal amount to move from up to down, but also by, say, an extra lattice vector, which would result in very huge values of the spontaneous polarization in a sort of quantized charge pumping sense. And if you're willing to let that happen, then in principle, you could have a nonpolar structure that applying a field and charge jumps by an extra lattice vector to bring it back onto itself. So none of these are prohibited by theory from existing, and none of them would work with this particular method but they would certainly be interesting. And if you have a material that you think follows these properties, you would have to do more intensive calculation than the sort of standard 1D switching path that I started describing in the beginning. So to compute the spontaneous, in summary, I'm going to summarize now. To compute the spontaneous polarization from first principles, one needs to make this branch choice. So the branch choice is less obvious in systems where the spontaneous polarization is comparable to or larger than the polarization quantum. This often happens in supercells or situations where the polarization direction is along shorter lattice vectors. So our method here efficiently reproduces the same results as the standard 1D switching path method, but only uses a single structural calculation plus some post-processing, obtaining the Wannier centers and then analyzing them. It also eliminates the need to identify an insulating path between up and down, so that usually you would need your whole path moving from up to down to be insulating everywhere so that you could get a reasonable value of the formal polarization. So we currently we're preparing a paper, and if you want to do this sort of thing yourself, I'll be releasing a script that will assist in the analysis of the Wannier centers, and I'll make that available on a web page. So thank you. Yes?
Not really understood how do you do in BN. That is, you don't reverse the structure, you only reverse the Wannier functions.
Well, I mean, if you...
the nuclei stay fixed and you...
No, the ions get swapped as well.
So you swap also?
Yes.
You swap everything?
Right, I sort of consider them as Wannier centers of a different character with different charge.
Including the nuclei. And then the second question, I don't believe that if you do that in reality, you still are in an insulating state all over along the
Right,
path.
so I'm not saying you are necessarily in an insulating state. I'm saying if you are in an insulating state, then you have to deal with a lot of dynamics that I can't tell you anything about.
I agree.
Yeah, so this is sort of a follow-up question to that. I was bothered by that also. So would you get the same answer if you took a path from turning the boron into carbon and the nitrogen into carbon and then slowly turning them into boron nitride? Would you get the same answer as the answer?
Wait,
in other words, if you take as your nonpolar reference C2 to replace boron and nitrogen by carbon atoms.
Okay.
Right, and now change the charge in your pseudopotential so that one carbon becomes boron and the other carbon becomes nitrogen.
So, okay, I mean, maybe I'm not understanding the question. If we had, I'll start, I don't think this is what you're asking, but if, we replace them with carbon, we would certainly get different answers because they'd have different charges, and I'm multiplying by the charge for when something moves. So you're saying if we replace the atoms but then change their charge?
Well, you're moving one. You're swapping the two atoms.
Instead of a physical motion, he wants to do a continuous transmutation. So
Right.
You
okay.
can imagine a continuous transmutation of elements.
Okay, so one element is turning into another element?
If you start with C2, that's a non-polar.
Mm-hmm. But I mean, but if we're just changing the chart, so. Okay.
I think we'll take that as an interesting thing to think about.
Yeah, that's something I'll consider.
But another question?
I think that the answer, you have a discontinuous because in diamond the wave function is centered on the bond. So instead in bottom nitride is centered on the anion. I think that doesn't work in that way. No, you don't.
But one detail with that is there's no way of tracking what happens to the ionic contribution to the polarization when you do this transmutation. It doesn't make any sense. So that's why I'm not sure. I think actually the electrons stay more or less. Well, I don't know. Something else?
I mean, again, I'm not saying this is a method that's going to rigorously apply to every possible structure as well. It's just if you're going to think about typical ferroelectric switching, and if you were going to do this standard 1D path thing on a typical material, you can do this and get the answer much more quickly. If you think you have some kind of very exotic path, then I said before this method won't work.
Well, suppose we have a material when the polarization is really big, it crosses a different range, all right? I just wonder whether you can modify your method by in your functional you minus a polarization quantum.
So you're saying
instead of you have in your functional you have a difference between up polarization and down polarization, down two states, right? If you minus another quantum, then you can cross different range.
I mean, so you're saying
I'm not sure whether my
so one, this method doesn't prevent you from obtaining the polarization of a material with a polarization larger than a quantum. I'm saying no one charge moves an extra lattice vector beyond what it needs to move between going from up to down. So you could still have, say, if 6 charges move by 1/5 of a lattice vector, then you'll have a change in polarization larger than the quantum. I don't know if that was your question or not.
Yeah, my question actually is in some material, you do have imagine, all right, hypothetical material, your polarization is really very big across two branch. Now, if you're using your method...
So if you have some exotic switching process that moves you from one branch to the next?
To another branch. So
right.
I just wonder what in your method, can you just slightly modify the functional? You have the up polarization minus down polarization minus a polarization quantum of integer.
Its functional is not up polarization minus down polarization. It's up 1A function position minus down 1A function position, which is
right.
not the same thing. But anyway, let's go. Ron, we're over time. So Ron.
Okay. So just quickly, so when you invert the structure, I mean, you have to choose a inversion center, right?
Yeah. Or yes.
Is it possible that there could be more than one choice?
Right. And so in a lot of simpler systems, the choice is somewhat obvious. I'm kind of currently working towards a systematic way to identify the best choice, and I guess I would say the choice that allows you to minimize this overall displacement is most likely to be the physical, to give a value that chooses the physical branch.
Okay, I think we should.
Okay.
Now we have John Hui Sung.
Do you need, I don't know what kind of adapter you need.
Yes, I think geometric and energetic properties of ferroelectrics and related materials in DFT.
Is he going to get a dongle?
Yeah.
Things. What's going on? I think I duplicate. Is it here? Not here.
You should pull this out and put it back in again.
Okay. This time works.
I think it's doing something. Oh, yeah.
Okay. 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 Thank you. So. First, I would like to thank the organizer to choose me to give this talk, and I also would like to thank you all to stay here for the last talk. I hope I can do good enough to make it worse for you. So first, my talk is about accurate geometric and energetic properties of ferroelectrics and related materials from an efficient density functional. So I'm actually new to this community, and I actually am a developer of density functional theory. So recently we construct a new and efficient functional, and it is good for various a variety of systems which has different bonds. So like covalent, metallic, ionic, hydrogen bonds, even the van der Waals bonds. So I think maybe this community will be interested in this functional, so I come here to present my result. So first, I think in the previous talks, people has already stressed the importance of the structures and energies for the ferroelectrics and other materials, since in many times you try to do DFT calculations to get the accurate structure and energies, either by fitting these results into more empirical models, or just use it to interpret your experimental results, or maybe you do high throughput searches for new materials. So I think I don't need to stress too much about the importance of this accurate first principles structures and energies. So, and currently, I think DFT is a workhorse first principles method due to its efficiency. And here I would say that the functional we developed recently keep the efficiency and meanwhile improves the accuracy a lot. So, but let me give you some introduction of DFT first, I mean, in case you are not so familiar with it. So the DFT, I mean, the Kongshan DFT, the total energy can be written as kinetic energy plus Coulomb energy of classic Coulomb energy of electrons, and the exchange correlation energy, which is the key for DFT, and you need to model that in order to improve the accuracy or keep the efficiency. So, and then there's the last thing is interaction between the electron and the external potential generated by the nuclei. So, and this is a Kongshan equation where this effective potential can be written down as this one, and the density can be written as the sum of the Kongshan orbitals. And this one I would like to stress, this kinetic energy density can be written, I mean, defined in this way. And this is a key property I will talk about today in terms of the constructing a new functional. So, and this exchange correlation energy can, this one is the only part to be approximate. And this can be categorized into this 5 rounds of the so-called Jacob's ladder. And the lowest 3 rounds are efficient semi-local functionals. LDA usually only uses density, electron density, and the GGA uses the density gradient, and the meta GGA uses the kinetic energy density. When you climb up from the meta GGA to the hybrid functional, so then the efficiency dramatically dropped. I mean, usually we can see that the accuracy from semi-local functional improves from, I mean, when you use hybrid GGA, usually you will expect improved accuracy in comparison to the semi-local functionals. So in this lowest 3 rounds, because this meta GGA use all the information is electron density, electron density gradient, and the kinetic energy density. So it's potentially the most accurate semi-local functional. But let's see first what choice are available now for the ferroelectric materials. So we see that LDA usually underestimate the volumes and also too small energy difference between the, I mean, for that double well of the cubic phase and tetragonal phase of like BATiO3. So, and usually people use LDA, I mean, with experimental volumes like the one we've seen in Valentino's presentation. And also, this is kind of a famous failure for this PBE for ferroelectric materials, which gives you super tetragonality. And because of this, and in 2006, I think Wu and Cohen, I mean, give the designed GGAs for solids, which gives you good geometries, but usually not satisfactory for energy. Let's see the energy difference between 2 different phases of the ferroelectric materials. And also later the PBE saw, so the version of PBE designed for solids also performs similarly with Wu and Cohen. And this in ferroelectric materials, I think this B1WC hybrid GGA is somewhat standard for the for the geometries and energies. So it gives you good valence, energy differences, and the polarizations, also band gaps. But the one problem is that this is computationally much more expensive. So today I'm going to present this scheme meta GGA. So it's so the performance is of a scheme meta GGA is comparable to B1WC for valence, energy differences, and the polarization. But for the band gap, of course, this B1WC will be better since this scan is still semi-local functional. And this scan is almost at GGA's cost. And it improves the band gaps in comparison to GGA. So let me show you some results first. So this is plot typical ferroelectrics PBD TiO3 and BaTiO3. So here I present the volume and the CA ratio and the polarization and the energy differences of the cubic and the tetragonal faces. So we can see from this volume, this red is scheme and this blue is experiment, and the B1WC is here. So and the PBE is here. So for the total volume, actually scheme is comparable to B1WC and the B1WC in terms of compared to this experiment. And for this CA ratio and this scheme is also good, right? So the problem in the conventional GGA for let's say PBE is that they are super tetragonal. So then this scheme performs reasonably good. So and then this polarization. So we have scheme here, and this scheme is here. So again, it's very good. And one more thing I would like to stress is this energy difference. So we don't have good experimental data for this energy difference, but we would like to use this B1WC as a reference. So we can see that this scheme is very close to the P1WC for these two prototypical ferroelectrics, BaTiO3 and PbTiO3. So this is a performance of scheme for these four properties. Now let me show you this band gap performance. This scheme is for these two systems consistently better than PBE, LDA, and WC. So we test a lot of semiconductors. This is actually the trend we see. So, but it's not as good as this B1WC in comparison to the experimental data. And this actually is what kind of we expect now for semi-local functionals. So now let me tell you something about the scheme. So what is scheme? So scheme is actually stands for the strongly constrained and appropriately known meta GGA. So it satisfies all 17 exact constraints that a semi-local functional can. So including all constraints satisfied by the standard PBE GGA. And appropriate knowns means that we use these knowns to guide the functional across constraints from one constraint to the other. And they are appropriate because those systems have exchange correlation holes that are localized, very localized. So then semi-local functionals should be able to give accurate total energy for those systems. So this is the basic ideas behind the construction of SCAN. So, and I would show you this, briefly, the accuracy for diversely bonded systems, which include covalent, metallic, ionic, hydrogen, and van der Waals bonds. So if you are interested in, you can take a look at this reference. So here I show you the performance of SCAN for the diversely bonded systems. Here the up left panel shows the energetic ordering of different ice polymorphs under different pressure. So from left to right, the density gets increased, and the van der Waals interaction gets more important. And we can see that the PBE and the PBE zero destabilize too much this high density state. But when you add this Takachenko-Scheffler's VDW equation, you can stabilize this high density states. And interestingly, this SCAN actually gives very good energetic description for these 7 polymorphs. And in the lower left panel, I show you this energy, the energy ordering of this silicon under pressure. So in the, David, how much? Half time. Okay, so then this, so anyway, so this SCAN gives you very accurate energy ordering for the silicon and also the energy ordering for this manganese dioxide for different phases. This is the only one that gives you accurate energetic ordering as well as lattice constants and magnetic structure and also band gap. So here I just briefly talk about why can SCAN describe diverse bonds. This is because this included kinetic energy density, which can help recognize different chemical bonds. And you can use this information to design specific GGAs for different chemical bonds, and then use an interpolation scheme to cover all the chemical bonds. So now here is a performance for the multiferroic, so BIF iron BIFeO3. So we can see that for polarization and then the magnetic moment, SCAN is here, so slightly overestimate, and then this volume, so it's here, and so the band gap, so the SCAN is comparable to this PBE plus U with U equal to 2. So this is pretty remarkable. So if you excluding this band gap, SCAN is the best overall, and SCAN is comparable to PBE plus U with U equal to 2 for the band gap. Here is just, I just got some new results from my colleague. So the first phonon dispersion relation for the cubic strontium and titanium oxide, and we can see that only SCAN can give you this phonon, so predict that there is no soft phonon in the gamma point for the relaxed structures or for the structures with experimental lattice constant. So we need to take a more look at this one, but the experimental results seem to suggest there's no soft mode in the gamma point. So here comes my conclusion. So SCAN is accurate and efficient for the electronic, for the ferroelectric and multiferroic materials. So systematic improvement over the GGAs and often comparable or more accurate than the P1WC hybrid. So, and there is my acknowledgement, and thank you for your attention. So,
you mentioned that you have the exchange correlation hole localized. What do you mean precisely?
well, so what I mean is in terms of, let's say, delocalized situation, right? So the stretched bond situation, like the hydrogen molecule ion, it's fully delocalized, right? In the dissociated limit. But around the equilibrium, this electron hole should be localized enough. But this system is not, we should not use as appropriate norms because it's still, the bond is still a little bit too stretched. I mean, the bond distance. And the one we use actually is the compressed argon-2. So push it, and then in the repulsion wall, then we found that there's, let me try to think, this, so this exchange energy alone can be very accurately reproduced. If you can reproduce this exchange, I mean, so the sufficient condition is that this exchange hole, if exchange hole is localized enough, then the exchange correlation hole will be localized, because correlation tends to deepen the exchange correlation hole, right?
Okay, I think we should go to Eugene and then.
Okay.
Okay, first small comment. PB0, for instance, perfectly reproduces phonon properties of strontium titanate.
So I didn't.
PB0 hybrid functional reproduces, perfectly phonon properties of strontium titanate. So it's not only.
Okay.
But
so
the question.
PBE is 0, right?
PBE is 0, yeah.
So you are reproduced. So there is no soft mode in the gamma point.
Yeah.
Okay. Yeah. This is good to know. I mean, so PBE0 actually is hybrid, so it's computationally very expensive. So what I'm talking about, this is just semi-local functional.
Okay, but the question: do you have some free parameters or not?
No parameters for experimental data. So this is, so we have parameters, but they are determined by first principles argument, and so I would say there is no empirical parameters.
Yeah, I think the produced style is to have as few parameters as you can possibly have. So as far as you can go in that direction. Yeah. Okay, I think we should thank Junwei and thank everyone in the session. Are there any announcements? I guess we meet in about an hour for dinner here. Is that right? Okay.
I answer your question.
First of all, do you compute the correlation hole? Your correlation hole is the one which came out from the